Hello everybody, I'm Dave Dugan. I'm the president of EBTRON. Today we're at Halter Ranch in Paso Robles, California. At the end of this presentation, we'll have winemaker Kevin Sass come on. Kevin, we call him Professor Kevin. Known him for quite a few years. He does a great job. We've sent you some really nice wine today if we were able to send to your state. If we weren't able to send to your state, get with your lawmaker, okay? Because we can't really do anything about that. But we're going to do our regular virtual holiday brand guest presentation, and then at the end you're going to get off a GoToWebinar here and go to meeting. You just go over to the GoToMeeting link that we sent you, and I encourage everybody to go to that GoToMeeting link, even if we weren't able to send you wine, because Kevin's really good. He'll give you a lot of information about not only Halter Ranch, but wine and winemaking in general. And I think for a lot of people, you'll enjoy that. You don't have to drink the wine that we sent you today. You can save it, but I still think that it's worth spending some time with Kevin. All right, so I'm not in Paso today. I am in Ridgeway, South Carolina. That's a little unfortunate. I was there last year, but I'm not there this year. And so I'm going to leave my virtual cave right now and start this presentation with you. Okay. Oh, one last thing. When you do come on later, while Kevin is on, turn off your video and turn off your audio so that he can go through his presentation. And then when he gets off, if you want to stick around and hang out, then you can turn on your audio and turn on your video. If you have questions for Kevin, do them through the chat and he'll answer you there, okay? Same thing kind of with me. If you have questions with me, because of the nature of this event today, I'm not going to do a Q&A at the end of this, okay? I have basically an email address you can send me questions to, but at the end of today's, we're going to move right over to the wine tasting. So I'm not going to have any time for Q&As. Okay. So, but enjoy it. And, hopefully, most of you I've seen, at a brand guest event or either in Myrtle Beach or in Park City or somewhere along the line. So, hopefully I'll get to see you all again in person next year. Thanks. Take care. Happy holidays. All right, let's get this thing started. Okay, so the idea here is that we do this holiday virtual. It's become kind of a regular thing since the beginning of COVID, and it's primarily for it's a VIP event, and it's for those of you that have either been to one of our virtual events before, or been to Brain Guest in either Myrtle Beach or in Park City, or some other event along the line. So because it's the holidays, I'm going to take a lot of breaks in between my material here. I'll be just going back and forth, and I've got some material that we're going to do that we've done, and I've got some new material, and so hopefully this works out for everybody, and we have a good time today. Okay, so the theme of my presentations are always why do we need to measure airflow rates in particular, and then why EBTRON, and that's going to be the same theme I'm going to carry through. All right, and most of you should know already a little bit about us, but I'll just do it real quick again. We started in 1983. I started in 1984 with Mike Urbaniak, who's still with us. We worked together, but we built a nice team of people up over the years. A lot of folks that EBTRON have been around for a long, long time, and that's really a great thing. We actually pioneered outdoor airflow measurement, direct outdoor airflow measurement in late 1980s, and that was a bit of a challenge, but that's what we did. That's kind of our claim to fame. I always laugh when somebody says, "Oh, you folks don't make a product specifically for outdoor airflow measurement." I kind of really chuckle a bit over that, since that is really what our claim to fame really is. We've done it with this advanced thermal dispersion airflow measurement. We'll talk about that a little bit at the end, okay? We are really a measurable difference. Now, the why measure airflow rates? Basically you break it down, and that's what we're going to talk about today. I break it down into provide acceptable indoor air quality. To me, that's one of the most important reasons. Improve system control, reduce liability, save energy, and monitor system operation. That's kind of where I break it down to. You can't manage it if you don't measure it, right? And so let's start with this provide acceptable IQ. I think that's a good place for us to start. We'll go through this, we'll take a short break, and then we'll come back and go through the rest. So basically, when it comes to indoor air quality, you're going to find, without me going through the details of this particular slide, outdoor air is paramount for indoor air quality. You need dilution ventilation. And when you take a look at the standards that we have, whether they be healthcare and non-healthcare standards, whether they be, around airborne infectious disease, the new standard 241, everything's really driven around airflow rates. And so I want to make sure that everybody always recognizes that, and that's what we're going to talk about. And then the other thing that's really important from an indoor air quality perspective is building pressurization. It's not just pressurization in healthcare facilities or labs, it's pressurization in all of your buildings, occupied spaces. It's just important, okay? And so I've always gone through these slides. I say, hey, let's understand the contaminants of the concern. And the reason that I do this is that they're not all from the occupant, okay? So we have to make sure that we understand that we have to take care of contaminants that are not sourced from the occupant. So, I've got building generated there with VOCs and other chemicals, and I have biological, and those biological ones have typically been moisture related, mold and fungal growth, for whatever reason associated with moisture. A lot of it is HVAC system control or lack of. Outdoor generated, what's going on outdoors. Do we have pressurization problems where we're bringing untreated outdoor air in before it ever crosses a filter? And then of course we have occupant generated. Typically it's been body odor. And COVID kind of changed that. We have to think about airborne pathogens. Let's face it, before COVID, we didn't really think about airborne pathogens unless we were in healthcare. Okay, so this is a little bit different, right? And so I like to use some real simple slides. Those of you that know me probably are tired of me saying I like to use real simple slides, but I do. Okay, and when we look at indoor contaminant basics, okay, this box represents an occupied space. If we didn't have any outdoor air or any targeted high-level filtration, meaning filtration that can remove what we are actually a contaminant of concern, what would happen if it was sourced within the space is the contaminants would build up, they'd get beyond a threshold level, and theoretically they could become dangerous. And it doesn't matter what the contaminant is. It could be a chemical, it could be mold, fungal growth, it could be airborne infectious disease like COVID, okay? So, what can we do about it? Well, I brought this slide back. I used to use this slide all the time, and I don't know why I actually took it out, okay? Because I was like, listen, let's remember what can we do? And I call it the 3 R's, right? Just for like we had reading, writing, arithmetic, which really wasn't right. I have, reduce, remove, and replace, and that really isn't necessarily right either. But it's close enough, okay? It's something that you can remember, and so that's the 3 R's. And then I tell everybody, I'm also a Rutgers University graduate, and I'm really kind of partial to the letter R. Okay, so you know, when we look at the remove, okay, we're going to remove contaminants with targeted filtration. Okay, and filters that can actually remove what it is that we're concerned with, and that's going to be always going to be part of our solution. Okay, and then when you look at it, you think about healthcare. We talk about, you know, total air changes per hour. We're talking about room air changes. How many times does the room change its air? And that has to do with how filters work, okay? All right, because that's crossing over the filter, okay? And so, you know, we have to think about total air changes per hour or room air changes per hour, okay? The other thing that we can do and the one that I focus on in my presentations, the other thing we can do is we can, you know, reduce our contaminants through dilution, bringing in outdoor air that is not contaminated, and then, you know, diluting the contaminants in the space, or dilution ventilation. And again, if we talk about, you know, what we're used to in healthcare, that's outdoor air changes. Okay, how many times does the room change its outdoor air per hour? Okay, and the combination of those two are what we've used for years in healthcare. Okay, and it's the same concept for occupied spaces, non-healthcare facilities. And so the reality of this all is that, you know, we're going to do a combination of outdoor air and targeted filtration, okay? And then we also can look at reducing the contaminant source to start with. All right, now you might be sitting there saying to yourself, well, you know, we can use UV light and all that. Well, yeah, if we're trying to, you know, take care of something like viruses, maybe we can. But don't forget, the two fundamental things that we have to do is we have to use high-level filtration, targeted filtration, and outdoor air. All right, if you want to add other things, that's fine. But this is the basics. And sometimes we lose sight of the basics, all right? All right, so when you look at Standard 62, you know, some presentations I go into a lot of detail, and others I don't. And this is going to be one of those where I don't, okay? You know, basically, I just want to make sure that everybody understands that there's two procedures in Standard 62, and both of them are built on ventilation rates, okay? So we have the ventilation rate procedure, and it's the prescriptive design procedure in which outdoor air intake rates are determined based on space type, application, occupancy level, and floor area, okay? And it's kind of a procedure for figuring out how much outdoor air you need, okay? And then we have the IQ procedure, all right? And the IQ procedure it's an alternate ventilation procedure, but it's still a ventilation procedure that shall determine the necessary rate of outdoor airflow to maintain concentrations of design compounds, particulate matter in the indoor environment at concentrations less than design limits. And it's based on indoor and outdoor sources, air cleaning, and other variables. And people are typically using the IQ procedure to reduce outdoor air, but that doesn't have to be the case. Okay, it's just, you know, when you're using the ventilation rate procedure, you're basically saying, hey, I'm not going to look at these contaminants. When you look at the IQ procedure, you are. You know, in the IQ procedure, you calculate the outdoor air requirements based on mass balance equations. But one thing that I'd like to point out to folks is that one change that has been made to the IQP in the 2022 standard is that there is now a verification requirement. There's an entire section, test section, it says verification of occupant satisfaction in indoor, basically design compounds concentration shall be performed after the building is completed. And I think that's really, really important for you to understand that there's a little more meat to the IQ procedure than there was in the past, okay? And there is a burden of proof that you've actually accomplished what you've wanted to accomplish, okay? Another thing that I'd like to just point out in Standard 62 is that, you know, there's a a requirement to pay attention to building exfiltration or building pressurization. And it says ventilation systems shall be designed such that the total building outdoor air intake equals or exceeds the total building exhaust under all load and dynamic reset conditions. So pressurization is a big deal, and it has the informative note that says net positive mechanical intake airflow for the building as a whole reduces infiltration of untreated outdoor air. Now, there's that exception that I kind of jumped over. Standard 62 seems to only be concerned with outdoor air coming into the building that has a lot of moisture in it. But the reality is pressurization can be a problem even in drier climates because you're bringing untreated outdoor air in before you ever pass over a filter. So just think about that, okay? When you look at, again, some simple diagrams, you know, what is a problem? You know, negative pressure is definitely an IQ problem, okay? And when you're cooling and you have negative pressure, you're transporting three things. You're transporting moisture, heat, and untreated outdoor air, dirt, dust, pollen, whatever's outside, inside. You know, moisture is not being, it's not being removed because it's coming in before it crosses a coil, as is the heat, and then the whatever is in the outdoor air is coming in before it ever crosses a filter. So that's an IQ problem, okay, potential IQ problem. When you're economizing, a lot of folks get sloppy when they're economizing, don't care too much about pressure as long as doors open. But I don't think that's really true. You know, that's not right. I mean, if you're economizing and your pressure isn't right, you're still going to have potentially perimeter temperature control problems. You're still bringing in untreated outdoor air, you know, in terms of dirt, dust, pollen, whatever's in the outdoor environment before it's filtered. So I do think it still matters. When we get into heating, it's the same potential problem, although when we're heating in real cold climates, pressurization gets real tricky, and I don't even want to talk about it too much because there's cases where positive pressure creates problems in very cold climates because of the moisture inside the building, okay? But the bottom line is pressurization does matter, okay? Other things that, you know, that I referenced in that first slide, the IDCC or ASHRAE Standard 189, they're essentially the same document. You know, the International Green Construction Code, there has been a requirement in it for, that says basically each mechanical ventilation system shall be configured to allow for the measurement of outdoor air intake for use in testing, balancing, recommissioning, and outdoor air monitoring is required. And it does actually require outdoor airflow measurement, okay? Standard 170, we don't do a lot of healthcare. I usually say to folks that are in healthcare that, hey, you know why you need to measure airflow rates, but it doesn't hurt for me to, you know, just quickly summarize how 170 is driven. I mean, you know, pressure relationships to adjacent areas. I mean, really, when you look at pressure control in healthcare facilities, really the best way to do it is by controlling differential airflow rates, because then you can compartmentalize building pressure. We talked about air changes, so you got minimum outdoor air changes per hour that you need to meet, as well as minimum total air changes per hour for the room. Those are things that really should be measured and controlled, okay? Even though we're not talking about it in any detail today, there is minimum filter efficiency, there is design relative humidity, and design temperature. All these things require that your HVAC system is being properly controlled and operated, okay? So, you know, that's 170. Most recently this year, Standard 241 came about, control of infectious aerosols. Basically, you know, a real quick way to look at ventilation in something like COVID-19, you know, airborne infectious disease. You have an infected individual in a space, they talk, they cough, whatever it is that they do, they sneeze, you know, around them is a plume of basically that comes off of them, can have some airborne infectious disease in it, and some of those larger particles will fall to the floor relatively quick, 3 to 7 feet, kind of what drove us for our 6-foot spacing. But other particles get desiccated for various reasons, and they don't fall to the floor, and they become suspended. And those are the ones that we really need to concern ourselves about, and those are the ones that we're going to, use our HVAC system to manage. Okay, Standard 241 itself, a real quick summary of it. It's built on top of the base ventilation requirements of Standard 62 and 170. It requires a building readiness plan when you go into this IRMM, infection risk management mode, okay? And basically, there's a lot of different ways that you can go about doing this. It's going to be a combination of increasing outdoor air flow rates. It's going to be a combination of increasing, air cleaning effectiveness and efficiency. It may be adjusting the population in the spaces. You may be doing things like UV light, but it's going to require. It's not just you just don't walk into a space and say, well, I'm going to go into this IRMM mode. It's definitely a control deal. And to be able to go from one mode to another, you're going to need to measure things, particularly airflow rates, okay? So, at any rate, that's what we're going to need to do there. And then there's a documentation requirement, okay? So that's 241. All right, whenever we talk about things like COVID, and we're going to understand a little bit more about why this might be later, but it's so important that we understand how important outdoor air is, okay? I mean, during COVID, most of us had no trouble, and I say during COVID, it is still during COVID, okay? But during COVID, most of us had no problem sitting outside. I remember going out and having lunch and beer and dinner, and it'd be 45 degrees out. I'd be sitting outside eating and drinking because I did not want to go into certain spaces, okay? And, there's a reason for that, okay? It's kind of infinite outdoor air. And then disabled demand control ventilation, because demand control ventilation, as we'll talk about later, has a lot of problems in terms of providing adequate outdoor air, all right? So that's something we want to think about too, all right? Non-healthcare facilities has been our recommendation since pretty much the beginning of COVID. It was like, we called it normal and pandemic mode, but we'll call it normal and IRMM mode to be, or an IRMM to be correct today. Normal mode operation on low occupant density spaces, we can make a very good argument that you should never do demand control ventilation, okay? That you should maintain the required ventilation for the maximum expected population, right? High occupant density spaces, even though we haven't talked about this yet, we're going to show you ways to improve DCV later today. And it's going to be by maintaining upper and lower airflow limits and potentially doing some other things to get you closer to meeting the ventilation requirements of your code or standard 62. In this IRMM mode operation, all occupant densities, we're like, hey, just max out your outdoor air, okay? And if you do it right, it's not just design outdoor air, it's above design, because there's going to be off-peak load cases where you potentially can bring in even more outdoor air. I mean, when we're in COVID at its peak, there is no argument anybody can make that bringing in more outdoor air, if it was properly conditioned and didn't cause pressurization problems, was not a good idea, okay? And then when there's an economizer, air side economizer, make sure it's working properly and switching over properly. And somewhat unfortunate, we've kind of gone away from air side economizers. I'm not saying we've gone completely away from it, but there's less of them than there were. There's a lot more DOAS. People make a lot of good arguments for DOAS. I get it, decoupling and things like that. But we really have now cases where we have less outdoor air coming into a building, and it'll be interesting to see how that pans out over the next few years, because DOAS is still providing minimum outdoor air, where airside economizers provide a lot more than minimum outdoor air, okay? So IRMM operation, basically we're saying is disable that black line if you were doing DCV, at least go to the design outdoor air and preferably go above it. And you're not going to do that unless you're controlling and measuring and controlling things, okay? So that's our, real quick IQ presentation. When we come back, we're going to talk about improving system control. And so I'm just going to kind of move over there for a couple minutes, and then we'll come back and we'll improve system control. All right? Thanks. All right, Jessica. Done with this part.
Oh, yay. Good to see you. Took you a while.
Yeah, I have a break.
Wine?
Yeah. Let me start the Morgan clock. Oh, all right. 5-minute break. All right. So I think that's what I'm going to do. A few of these 5-minute breaks. Those of you that don't remember Morgan's been in a lot of these virtuals. He kind of left us a couple years ago, but he's still around. I still talk to him every day. I have to decide if, as the day goes on, I might get my Morgan voice going, but I don't know. But right now, like, he's sitting here in the box, and that's his picture and footprint. So, So anyhow, 5-minute break, then I'll go back, and then we'll just, on the longer segments, I'll just keep coming back. Okay. So hopefully we sent you guys these classes. I'm thinking we did, but
All right.
I don't know.
Cheers.
I hope we did. They're unbreakable. They're great.
They are nice.
Yeah.
Just don't put them in the dishwasher.
Some of them can go in. Some of them can.
Oh.
It just depends. Well, no, yeah, it depends. They ship us different ones every time. It's the same company, but you have to look in the bottom. Sometimes they say dishwasher safe, and sometimes if they're not dishwasher safe, then you're going to end up with more than just that indentation on the back.
Yeah, exactly.
That indentation on the back is actually, it's supposed to be there.
What do they call that?
It's a finger thing.
Yeah, but that's not the right name. There's an actual name for it.
Oh, well, that's what I call it.
Okay, it works.
So hopefully you're all enjoying this break, but I'm enjoying this break.
It's been a long day for you, right?
Yeah, well, it keeps getting longer.
I know.
Kind of in the beginning now, but we'll see. It's like, it's a long 5 minutes. It's probably not a long 5 minutes for you folks. It's a long 5 minutes for me. So.
Into what, 3? 2?
Yeah, still got 3 minutes or so. Hey, Paul, if you're on the other end of this, I don't know if you recognize the little ornaments, but we
You've enjoyed them.
We actually like them.
Yeah, they're nice.
Yeah. So. Oh. This thing with Kevin should be really good later. We've done this quite a few times with him. I actually joined their wine club. I joined their wine club like 20 years ago and really liked it for the Syrah. And but everything he makes is great. Hey, we're down to the 2-minute warning here. But, the Block 22 Syrah that we sent, it's not their, that's like their top of the line Syrah. I'm surprised that he actually...
That one is really good.
Yeah, surprised he actually sent it, and the CDP is a really great blend. If you decide that you're going to taste the wines with Kevin, I'm certain if you're going to try them both, I'm certain he's going to start with the CDP, okay, and then do the Block 22 Syrah. So, and I like those guys. There's if you've been on these virtuals with me, you realize that there's a couple wineries out in California I really like. I like them because they make great wine. I like them because they're good people. Kind of a combination of the two.
Really good people.
And
It's tasty.
yeah, and they do have wine clubs. I think it's a pretty good deal. Somebody's calling us.
The timing is impeccable.
Well, they're gonna have to wait.
I guess so.
Yeah. All right, we're down to 1 minute. Hey. Da-da-da.
They don't give up easily.
No, it's probably your mother.
Probably. I was going to say that.
That's who it is. So we've got 1 minute left, and then we're gonna get going again. I guess I got to get up. And
Gotta move.
I'll get this when I come back.
If I don't get to it first.
No, you're not going to get to it. But I should probably just take it with me.
I'm not going to bother it.
Okay, so time's up. I'm going to get going back into my studio and finish this thing. Well, I'm not going to finish it. I'm going to do the next segment, and then like I said, on the longer segments, I'm going to come back, do it again. Should be able to get a couple, 3 of these in, and then we'll go from there. Okay, so all righty.
Back to work.
Yeah, you can hang out here or whatever. It's not as fun as it was last year.
It's not nearly as fun as being in the winery.
No, no,
Especially for me.
no. So I'm gonna kind of go. All right. I'll be back.
See ya.
Yeah. Oh, that looks cool.
Yeah.
Okay, this is definitely a better way for me to give presentations. It's a lot more relaxing. Okay, so now we're going to talk about improving system control. All right, and there's 2 things that I want to talk about improving, and that is outside air intake flow rates and building pressure. Okay, and I'm going to spend more time on the outside air intake flow rates than I am going to on the building pressure. Okay, so we're going to find that when we look at an uncontrolled outside air intake, okay, meaning just there's no active control, all right, no measurement, no active control, you're going to find that there's system effects, there's damper issues, and there's environmental factors, and that they're going to result in uncertainties of more than 50% of your desired set point when you're in minimum outdoor air mode. And you need to ask yourself why that is. And so we're going to actually take a look at that and see if we can help you understand what the problem here is. All right, and so we're going to start with a simple recirculating air handling unit. Okay, only has a supply fan. There's no active relief. It's got a fixed minimum intake damper, so there's no active control, nothing resetting it. Okay. And what's going to happen on these systems is that if you go from, say, we're set up now with design supply air and design outdoor air flow rate, as we reduce the supply air flow rate, the mixed air plenum pressure is going to reduce with it because it's a fixed orifice, your intake's fixed orifice, the airflow is going to drop, and it's going to end up dropping proportionally with the supply air flow. And you're looking at this and saying, well, this is an air handling unit maybe, and it's like, yeah, but it could also be it doesn't have to just be VAV. It could be multi-speed constant volume. It could be a fan coil. We can make very similar arguments if we're talking about DOAS systems serving multiple ventilation zones on a DCV system, meaning there's pressures that are changing. You cannot rely on fixed damper position, all right? And when you take a look at this example, I'm going to say, hey, the pressure drop across that intake system at design is 3/10 of an inch. So the mixed air plenum is at minus 3/10 of an inch, all right? And so that if I reduce my supply airflow from 100% to 60% of flow, you're going to see that the pressure is going to follow that square root relationship, and the pressure is going to drop roughly 2/10 of an inch in this example, okay? And that 2/10 of an inch drop corresponds to the same 40% reduction in flow on the intake side. It's not rocket science, it's pretty straightforward, okay? And it's pretty well understood. People seem to get it on VAV systems. They don't necessarily get it on all the other systems. Okay, they get it on VAV. We see a lot of outside airflow measurement on VAV and control. All right. The question is there, you know, something else can something else cause this 2/10 of an inch change? And what we looked at, you know, to start with here was the mixing box changing because the fan speed changed. But what if it's not the mixing box that changes? What if the outside of the building changes? In this case, the exterior surface pressure on that intake. What could cause that? It would have the same effect because you're still a fixed orifice. It doesn't matter what side the pressure changed on, the pressure drop changed. Okay, so we take a look at this with this 2/10 of an inch change. What else could cause that? Well, it's wind. And this is why I like to talk to balancers and commissioning agents, and they go in and do a lot of work on systems that don't have active control. I'm like, you know, you went out, somebody set this up, you came back, you checked them, the readings are totally different, nobody understands why, they're blaming each other. It's like, listen, the wind could have changed, okay? And here we look at going from an 18-mile-an-hour direct wind, which is a positive pressure on that intake system, to an 18-mile-an-hour crosswind, which is a negative pressure on that intake system, is that same 2/10 of an inch change. So if you went from one condition to the other, you would see a 40% change in flow, okay? And that's what I'm looking at here. But you know, basically the 40% change I'm talking about is when the supply fan isn't changing. So that, you know, if you look at this graph and you go to look at that horizontal axis, go all the way to the right there, which is 100, you know, that's design flow. Well, now if you combine that with turning down the supply fan, now the errors get even worse. And so your outside air set point may be that black dashed line, okay? But now as you're turning the system down, you not only have the wind effect that affects it at 100% supply or design flow, it actually gets worse as you turn it down. And so you could be anywhere between those two red curves. And that's a lot of uncertainty. You certainly don't want to have that happen, okay? And this is actually some data from our building. And basically the black solid, or the black dash line is the set point, what we were getting on a day when there was no wind. And then we came back on a day when we had a crosswind that we measured down the side of the building. And we took the data again, and the red solid line is basically the running average of that data. That shows you that you got this significant reduction in outside air just from this pressure change. And then the scatter is worth a quick conversation here. Wind going down the side of the building is not constant speed and constant direction. It's moving, you know, its magnitude and direction is changing. And so that when you take a look at those flow readings, they're varying too. And that affects the way folks need to do control. We tell control people all the time, you've got to slow the output of your control loop when you're doing outdoor air intakes because actuators can't respond to transient wind gusts, okay? And so that's a whole nother story, but it's worth putting in. But the bottom line here, what I'm trying to show you, it's just the wind alone on a fixed damper system, even at constant volume, changed significantly the intake flow rate. The next thing you have to consider is you got to consider stack effect. And folks think about stack effect and how it affects pressure floor by floor and high rises in particular. But, you know, it also affects the intake. If you take a look at this simple diagram, I have an air handler on the roof serving a 4-story building, but it's only serving the first floor. And what you see there, that vertical shaft, is just my return duct. I don't show it, it's supply duct. I don't want to complicate the slide, okay? So if this air handler was only serving the first floor, basically you have a big hole in the building, the return duct that's connecting the first floor to the downstream side of your intake. And so on a day when the inside of the building and the outside of the building are roughly the same temperature, there is no stack effect. But if you go to the winter condition here, where you have the column of air outdoors is much more dense than the column of air indoors, you have a positive pressure on the downstream side of that intake damper that's going to reduce the amount of outdoor air that comes in. And conversely, the summer, it's going to be the opposite, although not typically as much. Okay, and so the question is, well, when do you see those same 0.2 of an inch? Well, you see that same 0.2 of an inch on a 100-degree swing on a 70-foot low rise, 5-story building. And you might say, well, I don't get a 100-degree swing, my climate. Well, building needs to be a little bit taller, but it's not high rises, it's low rises. And when you take a look at this, we have very similar to what we saw before. You get this big change in outside air, particularly then as you turn down. It's bad enough on constant volume, okay? But now if you add variable speed, it gets considerably worse, okay? And so we have summer and winter. And now what you have to do is you have to combine the two. You have to say, well, I could have summer direct wind with winter crosswind. And it gets really, really bad, okay? In fact, I tell people all the time, you have no idea how much outdoor air you have coming in most of your buildings unless you're actively doing something to control it. Don't tell me you're relying on fixed damper positions, okay? It doesn't work, all right? And you're gonna have problems. And you might say, well, it worked, test and balance says it worked. Yeah, it worked the day they checked it, but it's not gonna work day in and day out, all right? It's a huge, huge problem, all right? And that brings me to two position. So sometimes folks will use two position and two position to compensate for fan speed changes. And then not exactly the same conversation, but the same logic, please listen to, okay, has to do with two position on DCV. Okay, so when we talk about DCV a little bit later, it'll make more sense to you. But, all these calculations are based on the flow coefficient of the damper. Okay, in this case, I have one flow coefficient of the damper. The damper's at design flow is in a more closed position than it would be if you were to reset it to compensate for the fan speed dropping. If you compensate for the fan speed dropping, the damper being more open has less resistance to flow. So that same change in pressure is going to be a bigger change in flow. Okay, and so graphically, I just show it. It's like, even if the damper was linear, which it's not, which is what I'm showing here, is the damper is linear, now you have these wind effects are much more significant as you turn down the supply fan, or as you basically open the intake damper, okay? And, wind pressure, stack pressure, and then you combine the two, and you don't know where you're at. And, you can be bringing in too little, you could be bringing in way too much, you could be freezing coils, you could have pressure problems. Operationally, this is a nightmare that you really cannot compensate for, and it's probably one of the best reasons, why you should always measure and control outdoor airflow rates. It's not just, people think about outdoor airflow and measuring it and controlling it, for air quality, but it's really, it's an operational thing, okay? I mean, you have to have control of your HVAC equipment. You have to get this under control, or your building's not going to work, okay? And so, the other thing is, if it's recirculating units, anything that relies on dampers, we have damper issues, hysteresis binding deterioration. Hysteresis is just, hey, the damper, I can bring the shaft position back to the same exact position, but all the blades don't come back to the same position because it's just hysteresis in the linkage, okay? Slop in the linkage. Binding, same thing. You can have really bad binding that gets so bad that you break linkage, or you can just have minor binding that affects how certain blades open or close. Deterioration, seals, they start to rot, fail, the opening changes. I laugh when I hear people say, I use actuator feedback to tell me that everything's okay. Actuator feedback doesn't help you on any of these, okay? Unless the binding's so bad, it can't turn the shaft. And most likely it's either going to break the linkage or slip on the shaft. So you're not going to know, all right? You have to be able to measure things. Okay, and this is some data from our building, and we have a pretty good damper. Actually, it's a Tamco damper, and all we did is we went from closed to 15% open and 100% open to 15% open. So we're going like from night setback to minimum, or 100% economizer to minimum. Okay, and basically when you look at it, the blue data set is night setback to minimum, the red data set is 100% economizer to minimum, and you get two distinct data sets. That's hysteresis. The actuator's at the same position. The feedback from the actuator is exactly the same, okay, but you've got 20% different flow depending on which direction you're coming from. It's totally ridiculous that we try to have these systems that just rely on very simple, feedback, like position feedback. It doesn't work. I get it, it's inexpensive, but it doesn't work. So what good is that? Okay, and so when you look at these outdoor air intakes, you have all these variations. You have flow variations as a result from the system effects, the fan speed, environmental effects, the wind pressure, static pressure, damper issues, hysteresis, binding, deterioration. Unless you get a grip and get control of this, measure and control of it, you're going to have a problem. Okay, so ultimately the logical conclusion should be you measure this. But don't just measure it for alarming purposes. If you measure it for alarming purposes, you're going to be an alarm all the time, and you better put the alarm where nobody's going to see it. You want to measure it to control it. And it's not just on your large VAV systems, it's on everything. Okay, and we need to get a grip on that, all right? And so, building pressure, I said I'd keep it kind of simple, and I always kind of keep it too simple. We're not pressurizing a building, okay? That's not what we're doing. We're creating a pressurization flow with a mechanical system, and it creates measurable pressure drops that you can measure with a pressure sensor. But it's really the pressurization flow is what we're trying to do on a building, and we want to isolate that pressurization flow. And the only way we're going to isolate it is by measuring it. And how are we going to measure it? Well, we're going to measure it by looking at the difference between the ins and the outs. And if I got more ins than outs mechanically, I'm positive. If I have less ins than outs mechanically, I'm negative. And, that's just the way it's going to be, all right? And so, and if I was the same, it would be net neutral. So, we're going to look at some control strategies now. Now, I want to step out again for a second. This time I'm not going to take a break. I'm just kind of go over this table here and do something. I'll be right back. All right, that worked. Okay, we're going to look at the measurement requirements and airflow control strategies, but we're not going to get into the actual sequences because of lack of time. And so what we want to take a look at here is air handlers, supply return, supply relief fan systems. That's why I showed the two fans. It's not that you have two fans, it's that it's one or the other, okay, typically is how you're going to do this. And for outdoor air, we're going to measure the outdoor air. So if you look there on the bottom of the little green thing, it says AMD, that's the EBTRON airflow meter, okay? So you're going to put in the outside air intake path. And we would recommend that when you get to really low flows on outside air intakes, particularly on rooftop, we're really talking rooftop units here. Rooftop units where the airflow meter is pretty much almost sitting on the roof. Okay, if the flow rates get too low, you get transient wind gusts that will actually false out the flow meter. The flow meter really needs to be installed upstream of the intake damper on a rooftop unit. And so upstream of the intake damper is downstream of the louver or the hood. There's not a lot of room. And so that the damper is typically in a fairly closed position. You get a lot of wind on the roof. You'll get air moving around that gets picked up by a flow meter that's not real. So we say, look, we really want you to try to keep these velocities up a little bit higher. We find that the minimum you should ever consider doing is 150 feet per minute. That doesn't mean that you're not doing some lower. It's just that when you get lower, you are going to get some false readings. Moisture eliminating filters on hoods, they help. Filters in general would help, but not enough people filter outdoor air. Anything that causes a mechanical dampening filter type thing to keep the wind down is an advantage, but again, we don't always do that. So when you can, and you're doing something like a custom unit, that's when we say, hey, go min-max, okay? Go min-max damper, right? So, but we want to measure in the outside air intake, and that's just bottom line, we need to do that, okay? If there's no relief at the air handler, we're actually going to use the outside airflow meter to control the pressurization flow. Because even though you might get better measurement locations and more accurate measurement in the supply and the return, when you look at the differential between the supply and the return, the error gets kind of inflated. So you're better off when you can, if there's no relief at the air handler, just using the outdoor air intake flow meter. Okay, when we are relieving air, we talked earlier about, we want to know the ins and the outs. But the thing is, you can't really measure the ins and the outs accurately enough to do differential flow control. Outside air, you get outside air on a rooftop unit, 5%, you're doing great, okay? 5% of reading. 5 to 10% of reading on a rooftop unit is a good target, okay? If you try to measure the relief air, you're going to have a random number generator with any airflow meter you put there. Okay, so that's really not going to work, even though that's the paths you want to measure. What you really want to do is you want to look at an alternate location that gives you the same measurement. And it's not that difficult, okay? I mean, I do this little proof for folks that don't understand it. It's like, look, see that little red flashing dot there? We can make an equation for that says that the supply airflow rate is equal to the recirculation airflow rate plus the outside airflow rate. And that's an equation, okay? And I can look at this other red dot and say, make another equation. It says, hey, the return airflow rate is equal to the recirculation airflow rate plus the relief airflow rate. So I get two equations there. I subtract the two equations, I still have an equation. And so outside air minus relief, which is what we want, is equal to supply air minus return air. So on a recirculating air handling unit, you want to measure in the supply and the return airflow paths. And a couple things come out of this that you should, if you haven't thought about it before, if you're not recognizing this, then sloppy fan tracking is going to be sloppy pressure control, okay? Because this differential is your pressurization flow. The other thing that's nice about this on a recirculating air handling unit is it's good for verification. If you have decent dampers and a good air handling unit, you can go 100% recirc, meaning close your outside air damper, close your relief air damper, go 100% recirc, and you can compare the supply flow meter to the return flow meter and see if you have some error there. Or maybe you have one of the flow stations isn't installed, it's installed in a less than ideal location. You can actually use this to adjust one to match the other. There's lots of advantages of doing this. And in all these cases over to the right, I'm showing you an air balancer or a flow meter on the toilet exhaust. Typically, we're going to go with air balance and fan status. There's a couple of reasons for that. One is it's just not practical to measure the exhaust airflow of every toilet system. And then the other thing is toilet exhausts are really dirty. And so you typically aren't measuring those. There are cases in high rises when we're going to measure it, and those we would talk to you about and special considerations for how we would do that. But in this discussion, we're not going to do that. Okay. But anyhow, that's where you want to do it. So, on a recirculating air handler, you're going to want to measure three flows. You're going to want to measure supply airflow, return airflow, and outside air, or at least minimum outside airflow. Okay, and that's what you want to do. Okay, I don't have time to get into the strategies and sequences. I do have it, but I don't have it today, and I don't really want to do it today anyhow. Okay, what I do want to say to you though is when you do this configuration, do not fall into the trap of controlling the return air fan. For instance, this is a supply return fan system, very specific to a supply return fan system. Do not control the return air fan to maintain the differential between the supply and the return, and simultaneously modulate dampers to control the outdoor air. They're both the same value, but instrumentation uncertainty will make this hunt. You don't want to do it. The way we suggest doing it, and I can show you the sequence if you want to know it, is we simply use the return fan. Say we use the return fan as our friend in a sequence with the outside air and recirculation air damper. We don't even typically there's no relief at the air handler here. It's the only, I didn't really spell that out. This is when there's no relief at the air handler on a supply return fan system. Okay, this is what we would like you to do. Okay, if it's a supply relief fan system, obviously you can't make the relief fan your friend when there's no relief. So, you know, everything we're doing is by modulating the outside air and recirc air dampers. Okay, when we get into active relief, all right. So this is a case, active relief, we're not necessarily economizing, we just have more outdoor air required and pressure. Okay, again, these slides, sometimes they look a little complicated. They're really not, you know, but whenever we have active relief, we're using that outside airflow station in combination with the intake and recirc dampers to maintain the outdoor air set point. And then we're controlling either the return fan or if the relief fan, depending on which one there is, to maintain that flow differential. The flow differential is your pressurization flow, and then the outside air is your dilution ventilation. And then up there on the top left, we show optional delta P or bleed sensor. We like to go 2 position on the relief damper. Typically, if you're doing this right, you don't need to have a pressure sensor there or a bleed sensor there, but it does help you when you go on as you switch over. Okay, so it's kind of an optional thing. We use it. It doesn't cost a lot to do it. You're making basically an electronic barometric damper. All right. When you're economizing, nothing's really different, except now the outdoor air is being driven by your supply air temperature requirements. The pressurization is being maintained by the differential. If you're doing anything with your outside airflow station, it's making sure you don't fall below the minimum. If you fell below the minimum, you'd have to obviously do some kind of preheat or something of the outdoor air or do some limits there. Okay, you don't want to ever fall below the minimum. That really affects people in very northern and cold climates more than anywhere else. When you have a separate relief fan system, you are measuring the intake and the relief paths. Now, I tell people all the time, and a lot of times people don't want to hear this, but it's like, this is really hard to do with a rooftop unit because you're probably not going to get accurate enough measurement of the outside air for differential flow control. Okay, and the same thing is often true with a relief fan. I mean, if it's a ducted relief fan, that's fine, but if it's a relief fan sitting in the ceiling, just a powered relief, it's not. Okay, I mean, you have to get accurate measurement to do this differential flow control. And so you might not always get that. Now, if you can, maybe you have a ducted intake and a ducted relief, you can do it. But we need to pay attention to that. I've walked away from a lot of jobs like this, and people are like, why? It's going to work better than anybody else's. And I'm like, yeah, it's going to work better than anybody else's, but it's not going to work good enough. So that's, I don't want to do it. Multiple air handling units. What I'm thinking of here is more systems that have air handlers on individual floors. We have a makeup air unit, 100% outdoor air unit serving them. These could be air handlers on individual floors. It could be fan coils on individual floors. It could be like VRF or fan coils. You want to measure the outside air and control the outside air into either each one of those air handlers or fan coils, because there's a potential that they're all varying, and they're varying with static pressure and those kind of things going on. So you want to get that under control. I don't recommend that you use a VAV box with, a differential pressure flow cross or flow ring, because I don't think it's a very good measuring device. This is a case where you put in one of our lower cost EBTRONs to control the air onto and off of, off of each floor, okay? Or into each unit.
All right, so that's what we're going to do there. And again, we typically aren't going to measure the exhaust, although there are cases on high rises where we're going to want to measure that exhaust, and we can talk about that in more detail, on a case-by-case basis. Okay, multi-floor central station systems. These are my least favorite. Basically, you have air handlers on one floor serving multiple floors below and multiple floors above. Most of the time when we see people do that, they're not paying attention to the return airflow rates, and they end up having big stack pressure problems from floor to floor. And so, we're like, hey, what we need to do there is we need to measure somehow you have to make a provision to measure the return air off the floor. It might be some kind of stub ducting system. It's a good application for our Air IQ, actually. Our combination, which is our combination damper flow metering package. But one of the things I want to caution you about, I show a flow meter on the supply side too. Do not sum up your VAV boxes if it's a VAV system. The measurement's not going to be accurate enough to use for tracking. Put a separate airflow meter on the supply side, okay? All right, and that's really what I want to make sure I point out and emphasize there. Okay, when we get into DOAS, I bet you as the day goes on here, I get a lot slower talking, but or a lot harder to understand. I'm not sure, but I know I'm doing this really, really fast. A lot of times I do it this way, so hey, I can come back and ask a question later, or I have a project coming up I want to talk to you guys about. It's really why we're doing it this way. When you get into DOAS, you really need to measure and control airflow rates. I'm showing basic energy recovery here, even though I don't show any energy recovery. But I have outside air, I have exhaust air. As a bare minimum, I need to have get that unit under control for the differential. All right, and it could be for a number of reasons. Okay, but one real common reason is just filter loading. Okay, uneven filter loading between the intake and the exhaust. You've taken the air that you used to use to pressurize a building, and now you're trying to recover the energy. So your margin for error on pressurization is very, very small. Okay, it almost turns into, it's like, yeah, maybe I have plenty of outdoor air for dilution ventilation, but now all that air I used to use to pressurize my building, I'm taking to recover the energy. So your margin of error for pressurization becomes very, very small. So you should measure that differential and really maintain it. So that's why I'm just showing here that you're maintaining, you're controlling the exhaust fan side of it, okay? When you get into multi-zone, whether it's just dumping into the zone or you're providing it to fan coils or whatever you're doing, you really need to start thinking about measuring at the ventilation zone. Okay, so you measure at the ventilation zone because what's going to happen, a lot of times you're doing this with some type of DCV, so you're varying the zone flow rates. As you vary the zone flow rate to one zone, it's going to change the flow rate to another zone. Okay, and so you need to you have to think of it like the way you look at this outside air path is really the way you look at a VAV supply side, okay, where you need these VAV boxes to get the flow rates constant to the zone. You're doing the same thing when you're doing DOAS. You need to think the same way, okay? And so you're gonna do it at the ventilation zone. You still have to think about, particularly if it's DOAS, that with DCV, don't forget to track the relief for exhaust side, okay? Because if you don't, you're typically going to set this thing up at design and cut back the outside air. You're going to run your building negative. And I got news for you. If you do that in climates, humid climates, you're going to end up with walls that are soaking wet in your spaces. So you need to get some measurement there. They're lower cost flow meters for us because they're made for smaller ducts, okay? But you want to at least do this, the same thing, if you take a look here, I'm showing measuring at the unit with the total outside air, if you're using good flow meters like ours, you can sum up the individual ones if you'd like, okay? So this is really doing the same exact thing. When you get into some really humid climates, you should think about controlling the flow into and out of the ventilation zone. Because just controlling the overall exhaust flow still may end up with individual ventilation zones being negative, and you do that in, I don't know, southern Florida or New Orleans or some of the Gulf states, even the Carolinas, you're gonna have kind of a bad day, okay? And so you want to pay attention to that. All right. Well, that was pretty fast. I'm kind of flying along here. Wait till you see how fast I do the next one on reduced liability. So again, I'm going to do reduced liability next, but I think it's time to take a really short, break. Okay? So I'll be right back.
So you're still there? Is there still any wine left?
Yes, I didn't bother. I thought about it, but not bad.
All right. Well, another 5-minute break to start the Morgan clock again, and keep doing this, I guess. So, anyhow, it's kind of interesting. I hope a lot of you are actually watching this presentation. So my normal brand guest presentation is like, I don't know, it's like a full day. Used to be a full day and a couple hours the next day, and next year it's going to just be a full day. And I don't know how I'm doing it, but I'm covering a lot of the material that I would cover at the normal brand guest. I know I'm talking really fast, and I guess there's nobody here. When I do them virtually, I don't really get sidetracked like I do when I sit down and just start talking. So, I guess that's what it is. I must just have a lot of hot air in me when I do those radio guests. So, I'm getting there now. So it's like, well, what do you think, Morgan? I do this every day. It's like, well, Dave, I don't have, your Morgan voice isn't good. You've been given a presentation? No, Dave. Okay, well, anyhow, Jessica thinks I'm absolutely insane because I actually, every day, I keep them right, I actually work right over here. And I have him up there and I actually talk to him every day. I guess there's something wrong with me, but that's all right. Those of you that know me know that's probably a fact.
I definitely wouldn't rule it out.
No, wouldn't rule it out. I don't think it was always this way. I don't know.
What do you mean?
Well, I don't know. I don't think it was always crazy. When I was younger, I was different, I think. You didn't know me then.
No.
No, it's a good thing.
Probably.
Probably wouldn't be married. Anyhow, so I'm just going to sit here again and wait. These 5-minute breaks are probably not bad. They're good timing. As I get through this, I kind of figure out when I can or can't do breaks. Since this is kind of like supposed to be a festive webinar, I think, I want to squeeze them all in, because this is kind of like our holiday party. It's not really a party, but it's kind of like a holiday party.
Not super exciting.
No, well, not really. We're the only ones here. In the past, if you've been on any of these in the past, we've had some big days at Alter Ranch, and
We have. A lot of fun.
Really big days. And I would say this is going to be one of the more tame afternoons for us. So hopefully you folks are being tame too. Okay. So anyhow, we're down to the 2-minute warning again, and I'm going to go back and do another segment, and then I'll be back. I'm going to have to get my glass full.
Oh, work on glasses.
Yeah. This doesn't work. So, just hang in there. This isn't working at all. Okay. Not too bad.
No.
Okay, one more minute. One more minute, we'll get back and do it again. We're exciting.
I was saying the same exact thing. I was like, well, 5 minutes can be a long time.
That can be a long time. Yeah, we're exciting.
Nothing stand out here.
No, not really. Oh well.
They'll probably be happy when it's time to get back to work.
Yeah.
Just like
I really doubt during break they're actually sitting there listening to us anyhow. So I would, they might. I don't know. Are you sure when you get on with Kevin at the end, you use the chat and ask him some questions? He's really a smart dude, and knows what he's doing. I don't know if he would tell you, but he was a winemaker at Justin before he went over to Halter. They're right around the bend from each other, and I guess he's been at Halter now for like 12 years.
It's a long time.
Yeah, so it's pretty good. I love going out there. It's a great place to go visit. It really is. If you do go there, let me know you're going. I'll send them an email. I don't think it can hurt.
We've had several people do that.
Yeah.
I think it's worked out pretty well for them.
Yeah, I don't think it hurts. Okay. All right. Here we go. Let's try this again. See if it works out. Okay. All righty. Well, now we're going to talk about reducing your liability. And I used to spend a lot of time on this until I kind of realized that I don't really need to spend a lot of time on this. Okay. And so, on the liability side, to me, it's all about being able to demonstrate that you've met code, and that you have met the ventilation standards that are out there. Okay, it's really pretty simple. But it's not just that you've met them when you've turned the building over, it's that you can demonstrate that the building is actually operating to the code required ventilation down the road, or standard required ventilation down the road. And the reason for that is, you might say, well, I don't have to do that, but the building could end up being in some kind of litigation at some point. And really what could happen is that, either the owner or the operator changed the way the building operated, which is pretty simple, pretty common, okay, after you turn it over. You want to have some way to demonstrate that, that actually happened. Or something else changed, or you just want to show that, no, hey, I am providing code level ventilation, and there's, if there's a problem, it's not my problem, okay? And so when I look at this, I'm like, we have various codes throughout the country. We have the IMC, we have the UMC, we have Title 24 out in California, we have a variety of local codes, but all these codes are really driven around ventilation rates. And when you look at Standard 62, okay, Standard 62 drives the IMC, the UMC, and
California's mechanical code, part 4, okay? And so basically it's the ventilation rate of standard 62. And if you can, with the exception of California, you can use the indoor air quality procedure and say, hey, I made a decision to do something different than the ventilation rate procedure. But again, it's all based on ventilation rates, and you want to be able to demonstrate that not only did you provide the code required ventilation when you turn a building over, but after it was operating for several years, that either it's still doing that or somebody changed it, okay? People say to me, I don't care about standard 62. You should, it's what your code is driven around, okay? Your code is based on standard 62, okay? Unless you're in California. In California, like I said, standard 62 drives part 4, but most people in California are concerned with Title 24, part 6, okay? Which is the California Energy Code, which is different, but again, it's still based on ventilation rates. So, why I say this is a very simple presentation for me is I can sit here right now and I can go through what the code language is and tell you how to figure things out, but you're going to end up having a ventilation rate that you need to provide. And I don't care if it's from the ventilation rate procedure, I don't care if it's from Title 24, Part 6, I don't care if you did the IQP. You have a ventilation rate that you need to provide, all right? So you're going to need to measure it and control it to make sure that you're always providing it, and you're going to want to use that for documentation to show that nothing changed. That's as easy as I can make this, okay? And hopefully you all understand it. Now, I told you that would be fast, and that really is extremely fast. Would I do it that way if it wasn't this VIP deal where I want to go walk over there and, take another quick break? Well, yes, I would. But in this case, I'm just going to go over there and come back. We're not going to take another break right now, okay? I'm going to take my little quickie and come right back, all right? All right, now we're going to talk about saving energy, okay? Everybody seems to be concerned with saving energy, and I think that's a good thing, but sometimes we do it at the expense of the occupant. But anyhow, let's talk about this a little bit. Basically, we're gonna talk about saving energy in terms of we're gonna stick with outdoor air, because that really is what is one of the primary costs, energy consumers in your HVAC system. Okay, so we're going to talk about two things. We're going to talk about basically when you just have design, when you're trying to maintain design outdoor airflow rates, which is typically what you're going to do on low occupant density spaces, and then we're going to have quite a long discussion on demand control ventilation. Okay, and so if you recall from our earlier presentations, we've talked about factors that influence intake flow rates, and there were quite a few. And there was system effects that included fan speed variations, environmental effects, wind and stack pressure, along with damper issues, and you had dampers, which included hysteresis binding and deterioration. And we basically demonstrated that these factors could result in easily being in error by more than 50% of your desired set point when you're in minimum outdoor air mode, and that's not acceptable. And I don't really spend a lot of time here. I mean, you don't have to be a rocket scientist to realize that if you're bringing in more than 50% of what you intended to do, that's going to be costly. It doesn't matter if you're, what you feel like the cost of outdoor air is, whether it's $1 a CFM per year or $2 or something, or even more, depending on how you look at it. you certainly don't want to be off by 50% or more. So I don't spend a lot of time on this, what I call fixed set point outdoor airflow control or design outdoor airflow control, because we know there's a lot of variability there and we really do need to get this under control. What I want to spend more time on is demand controlled ventilation. So let's just look at this real quick. I've been around for a while, and when we were in the outdoor airflow measurement business and trying to promote it in the late 80s, early 90s, we were running into a lot of brick walls. People didn't care. Even though we knew there were a lot of indoor air quality problems, we just simply couldn't get anybody interested. And then in the early 2000s, we started to see a lot of publications about air quality. And this one in particular piqued my interest because it was not just an industry article, it was a mainstream article, and it was a cover story article. And this was in Business Week, and June 5th, 2000, is your office killing you, the dangers of sick buildings. And that really got people starting to think about indoor air quality, and in the early 2000s, we did a lot of work in terms of improving air quality in buildings, bringing in the proper amount of outdoor air. And then no sooner did we do that, and we started the energy folks started to say, hey, we need to bring in less outdoor air because it's expensive. And that's been happening now for the last 20 years. Okay, so that brings me to demand controlled ventilation. So what is demand controlled ventilation? Demand controlled ventilation is defined by Standard 62, okay, and it's permitted as an optional means of dynamic reset. And the actual definition of DCV isn't what a lot of people think. A lot of people think it has all to do with CO2. And really, the definition of demand controlled ventilation, or if you're in compliance, it says for DCV zones in the occupied mode, breathing zone outdoor airflow shall be reset in response to current population. Now, we seem to be always doing this with CO2. In fact, Standard 62 just approved its addendum AB, which is really heavily driven on maintaining CO2 levels. But the fact of the matter is, CO2 doesn't tell you what the current population is. So, we're going to have to take a look at that. And that's what I'm going to spend the bulk of this presentation on, and then we're going to talk about methods maybe to improve it. And there's also a minimum requirement. And for DCV zones in the occupied mode, breathing zone outdoor airflow shall be not less than the building component, which is based on the floor area for the zone. And I put in parentheses there, or that required by building exfiltration or pressurization, which a lot of people seem to ignore, okay? You don't want to let your DCV outdoor air ventilation go below what you need, for instance, to make up your exhaust, okay? So that's the definition of demand controlled ventilation. The addendum AB maybe changed some of the numbering a little bit here, but it hasn't really changed this concept, okay? So when you take a look at this, what we need to do is we need to say that, if we want to know if we're in compliance, we're going to look at the breathing zone outdoor air. We're not going to do it based on the number of people in the ventilation zone during typical usage. Let's take that out. And we're going to look at it based on the current population of the ventilation zone, based on what the definition that we just went through. Okay, so it kind of turns Standard 62 into an operational standard. So the question is, what in the world does CO2 have to do with this? And what is CO2? How does CO2 relate to indoor air quality? Because I've been doing this for a long time. I mean, I've been focusing on CO2 and outdoor airflow rates, since the early 1990s. It basically was, for me, I saw, two populations of people that think it's all about outdoor air flow rates, and then there's another group of people who think it's all about CO2 levels. So let's go into this. Why do I maintain CO2 levels? And I think this, like I said, I've been doing this presentation now for almost 30 years, very similarly to what I'm going to do today. I think that over the years, I find more and more people are getting, on board and understanding this, but I still run into way too many people that don't. So I'm going to keep doing this until I feel like until we get everybody on board, okay? So why am I doing this, okay? Well, first of all, we're not doing it because it's a contaminant, and we're not doing it because it's a direct measure of indoor air quality. That's one of the first misconceptions that I see. In fact, if you look at CO2 as a contaminant, basically OSHA doesn't consider it a contaminant until it exceeds 5,000 parts per million over an 8-hour period, and in shorter periods, even higher levels, like 10,000 parts per million over a 1-hour period, is where it becomes a problem. That's not where your buildings are. Your buildings are running anywhere from ambient outdoor CO2 levels of 400 parts per million to maybe on the high level, 2,000, 2,500 parts per million. So it's not a contaminant. So what is it? Why are we doing this? Okay. And the way that the industry has looked at this, and this is not correct, the way the industry has looked at this over the years is they said, hey, well, let's assume that we're at steady state. And steady state just means that nothing's changing, meaning that the outdoor airflow rate coming into the space is not changing, and the occupancy is not changing, and their breathing rate is not changing, okay? Their CO2 production rate is not changing. And we all know that when we're doing DCV, we're doing it because the population is changing, all right? Nonetheless, this is how the industry has looked at it. If you really want to look at this properly, which we're going to do at the end of this segment here, we're going to look at how the rate of change and the fact that we're not at steady state really affects how much ventilation we're getting, okay? But we're going to do this like the rest of the world looks at it right now. We're going to look at it at steady state, and I've read a lot of papers and I've seen a lot of things where people have used a steady state assumption improperly, okay? And I'm not going to go into that today, okay? Particularly on multi-zone recirculating systems, okay? But when you do a steady state analysis, the volume of the space no longer matters and the rate of change no longer matters. And to make a steady state equation, it's pretty easy. The goes intos have to equal the goes outos. All right, so that box there represents our ventilation zone, and that down arrow is our outdoor air. It doesn't matter if it's coming in through a recirculated system. It wouldn't matter if it was multi-zone. It doesn't matter if it's DOAS, okay? The deal is that we would have to know how much of the actual outdoor air is coming into that zone. So you have this one goes into CO times VOZ. CO is the outdoor CO2 concentration. Most of you think of it in parts per million. I put it in as cubic feet of CO2 per cubic feet of air. It has to do with keeping the dimensionality of the equation nice and clean. Same result, no difference. And VOZ is the outside airflow rate in cubic feet of air per minute. So that's it goes into. Another goes into, which is dimensionally the same, is G times P. In this case, G is the CO2 generation rate of the occupant in cubic feet of CO2 per minute, and P is the number of occupants. We produce CO2 as a byproduct of respiration. The more of us that there are in the room, the more CO2 there is going to go into the room. So there are two goes intos. Now we only have one goes out of, and the goes out of is the same amount of outdoor air that has come in is either going to be force exfiltrated, mechanically relieved, or mechanically exhausted. So VOZ is going to be the same, but now it's going out of that ventilation zone at the new elevated indoor CO2 level, or what you would measure theoretically what you would measure in the ventilation zone, so CI. So now you have an equation, okay? And we can take that equation and we can rearrange it algebraically so it's still an equation. And one of the things that we can rearrange it for is for VOZ over P, which in the units that an IP units, that's outside air CFM per person. So it's like, oh, got it now. I hope you got it now. You're not measuring CO2 because it's a contaminant or a measure of air quality. It's just simply a proxy for outdoor air CFM per person entering that ventilation zone, and there is value to that, okay? And as long as we know the CO2 production rate of the occupants, G, and the difference between the indoor and outdoor CO2 levels, we can make an estimate of how much outdoor air CFM per person is coming into the space. So graphically, we can do this, okay? We can say, hey, that blue line, which corresponds to the right vertical axis, we're at steady state, we maintain 1,000 parts per million. For a given population, which is the horizontal axis, we can now make an estimate of how much outdoor air is actually coming into that ventilation zone. And so that red line is the theoretical outdoor air coming into the ventilation zone. It's associated with that left vertical axis. And, I know when you look at these, sometimes it's hard to see these graphs, but that's why I give you a presentation to look at another point, or look at now if you're following along. Okay, but these are all based on CO2 production rates of the occupant, okay, and also being at steady state. All right, now the first problem that we have, which has been a problem that we've had since 2004, okay, in 2004, Standard 62 changed the way that you calculate ventilation rates from a simple CFM per person to CFM per person plus CFM per square foot. And over the years, I've heard people say, I do CO2 DCV because it complies with Standard 62. It really hasn't. Single set point, which is what most people are doing, hey, I keep 1,000 parts per million in a space. Single set point DCV does not comply with Standard 62. It overventilates on the high populations. In this case, I'm using a school classroom, 1,000 square foot classroom, and it'll overventilate on the high end and underventilate on the low end. Technically, overventilating is in compliance with Standard 62, but you really didn't, I don't believe that was your intent. In fact, I like using this slide quite a bit for those of you that do fixed set points, 8,000 part per million control. You have some real design problems here, okay? Because unless you're in California operating under California's Title 24, which is a little bit different than in the ventilation rate required, just about everywhere else in the country is using ASHRAE 62 ventilation rate procedure ventilation rates, or IQ procedure ventilation rates, which are even lower. Okay, so what I'm going to do here, taking a look at this slide, is I'm just going to use the default occupant densities for 3 types of spaces that are high occupant density. So I have a classroom, I have a lecture hall, and I have a conference room or a meeting space or a space of worship, okay? And at that occupant default density, okay, the calculated outdoor air required at that design occupant density for the classroom is 13 CFM per person. For the lecture hall, it's 8 CFM per person. And for that conference, meeting, or worship space, is 6 CFM per person, okay? But so many times I see folks say, okay, in these spaces, we're going to maintain 1,000 parts per million. Well, 1,000 parts per million, I'm using adult males 20 to 60 years old, and it's good enough for this example, is roughly 17 CFM per person. So at the design population for those spaces, okay, you are trying to force your system to provide considerably more outdoor air than you designed it for. So if you look at that classroom, 13 CFM, you're trying to push 17 in. The lecture hall, 8, you're trying to push 17 in. The conference meeting or worship space, 6, you're trying to push 17 in. What does that mean on a peak load day? It means that you can't condition the outdoor air. And in fact, when you get east of the Rockies, and we have a lot of moisture east of the Rockies, and the further south we go, the bigger the problem, we basically end up with temperature and humidity control problems, pressurization problems, operational problems. Folks don't understand. Why do they have water carryover problems in some of their intake louvers, particularly when there's not an economizer? What's wrong here? Well, what's wrong here is that the two things don't go together, okay? The CO2 level in the space and the outdoor air CFM per person, they're kind of codependent. You can't talk about one without talking about another. All right, and then during COVID, when folks changed they said, hey, we're not going to do 1,000 parts per million because 800 is better. Well, think about it. Now you're going to 800 parts per million. That's about 24 CFM per person in this example. Now you've even made your systems have bigger problems. Okay, now the folks that are in dry climates in the West don't necessarily understand this problem, but the rest of us do. okay? And so that's a problem. Then look at other things like, hey, you know, I use the IQP to reduce outdoor air, and I'm still trying to maintain CO2 levels. Well, obviously that doesn't work either, because you're lowering the ventilation rates even more. You might have that classroom, instead of being 13 CFM per person, 8 CFM per person. If you're trying to drive, you know, maintain 1,000 parts per million, you're still trying to drive 17 CFM per person in. So it's a huge problem. I've been talking about this for years. The people that I get in front of and talk to finally understand some of their operational problems. And this is one of the reasons why Standard 62 is trying to make some changes through their addendum AB. I don't think they did a great job, but I think that they had to do something, okay? And that's just my opinion about them not doing a great job. I think there's a bunch of errors that I'm going to try to point out a little bit later, all right? Those of you in California, you're a little bit closer, because California's 15 CFM per person requirement is closer to the 17 CFM per person. In this case, you're really not in as bad a shape, okay? The problem now comes is about assumptions. You've made assumptions. And how do these assumptions affect ventilation? And I was really, really happy about 5 years ago, because there was an appendix in Standard 62, Appendix D, and I thought it was misleading, and it got removed, and they came out with this original addendum AB, which said, hey, you know what, there's a lot of things that affect the CO2 production rate, which essentially affect how much outdoor air is coming in, and you need to make corrections for it. And the original addendum AB was great. It was said, hey, make these corrections, determine your set point, and, you know, that's how you're going to move forward with this. Well, over the years, we had, you know, the first AB did not get approved, and there was a second AB that didn't get approved. Finally, this third AB that did get approved really is a really, really bare bones version of this. But I want to just show you this because you may or may not realize it, okay? And so the CO2 production rate of an individual is based on a lot of different things. It's based on their age. It's based on their sex. Are they male or female? It's based on their diet. You know, are they high fat, low fat? It's based on their body mass. It's based on their activity level. And what I'm doing here is I'm holding, you know, all males, same diet. I'm using the average body mass for that age group, and I'm keeping the activity level the same. That's 1.3 MET. There's folks that say, well, you know, the younger people are more active. You can say that, but I've been in the classrooms where the 5-year-olds are napping, so I don't know that I necessarily agree with you. But anyhow, all we're going to do here is vary the age. And so we're going to calculate the CO2 production rate for each one of these ages, which you don't have to get too bogged down on this. The next column here is if I hold a difference between the indoor and outdoor CO2 level of 600 parts per million, and in this case, I'm just going to say, hey, the outdoor CO2 level is 400 parts per million. So that's 1,000 part per million nominal set point. How much outdoor air would I be bringing in for each one of these different groups of males, okay? And the 20 to 60-year-old males, there's not a whole lot of variability here, 16.4 to 17 CFM per person. The average being 16.8. I mean, I don't think that's a big deal. But when you look at the 5-year-old, it's 8.6 CFM per person. And then it gets a little bit better. And graphically, I think it's better to look at it this way. So the black line is what you needed to do to be in compliance with Standard 62. And yet if you had 5-year-old males in there, you're underventilating by 36%. And I've always said to the school people, I said, did you realize that when you mandated 1,000 parts per million, you were actually mandating underventilating your young your children in schools? Is that really what you wanted to do? And of course, they say, no, I didn't know that. Of course you didn't know that. Because it's not been something that's been highly publicized over the years, okay? So at any rate, so you have this problem that has to do with the CO2 production rate just based on age, okay? And actually, this is where California, Title 24 folks, it's actually worse. The underventilation is worse because your ventilation requirements are actually a little bit higher, okay? So it doesn't matter where you are, this is a problem, okay? Activity level is the same thing. You know, this is a very difficult slide to see if you're watching me, all right, because everything's so small. But basically, sitting quietly, 1.2 met for males, office workers, 1.3 met. Females are a little bit different, but you might have done the CO2 DCV in a workout space. So calisthenics, vigorous effort, 8 met. Okay, you might say, well, I want more outdoor air, but I don't think you wanted this much more outdoor air, because when you look at this relationship, you find that the met activity level is directly proportional to this to the CO2 production rate, which is directly proportional to the outdoor CFM per person. So it's 6 times more. And I'm not very good at math anymore because I use my calculator and computer, so I'm going to just say, hey, let's just say at 1.2 met it was 15 CFM per person. At 8 met, it's basically 6 times that, or 90 CFM per person. You did not design your system for 90 CFM per person. Sorry. Okay? In fact, when you look at activity level and you graph it, and I only go to 5 met here, you know, I used to say to people, you might as well go to Vegas and play one of the games. You have a better chance of winning the game than getting the ventilation right. And I actually had this graph in a paper that a little different data, but very similar, in a paper that I tried to publish in Ashtray Journal in 2010 or 2011. And they didn't want to publish it because they said I was CO2 bashing, even though it went through peer review and was technically accurate. What do you think about that? Okay? Nobody has any agendas in this business. But anyhow, I would say Dave Bitterman, party of one. Yep. Anyhow, that's the way it is, you know. There's a lot of uncertainty here. Okay, same thing's true with California's Title 24. Okay, then the next thing you got to look at. Okay, so I'm isolating uncertainties here, and okay, so now how does CO2 measurement error affect ventilation? I mean, basically, Standard 62 requires that you're within 75 parts per million, and on the CO2 measurement in the space, and says you can assume 400 parts per million outdoors. Well, I don't have time today to go through all the data, but I have data that shows CO2 levels outdoors anywhere from 350 parts per million to 550 parts per million, depending on the season, depending on what's going on. There could be a thermal inversion. There's a lot of things that affect CO2 levels, time of day in cities based on vehicles. A lot of things affect the outdoor CO2 level. Indoor CO2 level, it's not just the measurement error of the sensor, it's the placement of the pickup point. If you come to EBTRON, we have a brain guest room, we call it. It's a 5,000 square foot space. I have 12 CO2 sensors in that space that when they're together read relatively the same, okay? But operationally, when I put people in that space, those 12 CO2 sensors can read 100 to 200 parts per million different just based on where they're located, okay? And that has nothing to do with the measurement error of the sensor, okay? So this graph here that shows the scatter is basically what happens if you recalculate everything, but you had these errors in your measurement. So where the red line had been your theoretical ideal line, okay, the red scatter is with the 100 part per million uncertainty on the indoor CO2 measurement and 50 part per million outdoor. And this is if all of your other assumptions are right, meaning that you're at steady state, which you're probably not, that you actually knew the CO2 production rate of the occupants, which you probably don't. Okay, all right, and so you know those are the problems here, all right, and so so lots of us. I mean, look at that. The black is what you needed to provide. Okay, so that at 35 students there on the far right of that horizontal axis, you know, the black intersecting point is how much outdoor air that you needed to bring in, and the highest point on the scatter is how much outdoor air you may have brought in or you would be in CO2 alarm, and that's 50% off. Your systems can't handle 50% over ventilation. I mean, you might say, oh yeah, that's great, I don't mind the over ventilation. Well, your system can't handle it, okay? It wasn't designed to handle it, all right? So you got wasted energy, you got thermal comfort issues, you got pressurization problems, and on the other end, you might have IQ problems or pressurization problems, okay? And same deal here with Title 24. It's just, it's not a good situation, okay? Wasted energy, thermal comfort issues, same deal, okay? All right, so now you say to me, Dave, you've been fighting this for 30 years. I'm not going to fight this. I have to do this. You know, I have to use CO2. So what are we going to do here? Okay, so the question should be, can I improve it? All right, and the answer is yes, we can improve it. Okay, and the first thing you need to do is account for activity level and age, and then you need to set some limits. Okay, now how do you set limits? Okay, and most people set limits with fixed dampers, but we can demonstrate that fixed dampers, you have problems with them, whether they're on recirculating air handling units or you're doing DOAS with zone level measurement. You can't rely on a fixed damper position, okay? All right, there's just, on recirculating units, basically we have wind pressure and stack pressure that we have to deal with. We have hysteresis, binding, deterioration of the damper. Those are problems, okay? And then, we don't have the wind and stack pressure problem when we talk about DOAS, but on DOAS, we have different zones, ventilation zones, that are changing their ventilation requirements so that a given damper position will result in variability in airflow. So you just can't set fixed damper positions, right? So I show all this uncertainty on the damper, it's useless. And I'm not even showing you, like on a rooftop unit or something like that, the fact that there's additional error because test and balance can't even get out there and get a good measurement, okay? And then on top of it, you have this either changing fan speeds or changing damper positions on DOAS. So fixed dampers don't work. It's a moving target. You cannot rely on fixed dampers, all right? The way you need to do this is you need to do flow measurement. On recirculating units, it's in the outdoor air intake, and DOAS, it's at the ventilation zone, okay? And a very common way that people would do this is they would do a deadband control where they would set a min-min and a min-max, and they would control at the min-min or the min-max, depending on what the CO2 level in space is. And if you're doing it with airflow measurement, it's a big improvement. Now, I am going to show you some of the real-time lag problems, but it's a major improvement, and that's what you should really do. The preferred way that we've had to do it for years, that I think in reality, Standard 62AB is finally saying to do this, even though they don't explicitly say it. This is what they're saying. Okay, you measure the CO2 level in the space. Okay, and you look at your CO2 set point that you're trying to get to or not exceed, okay, and you basically, it goes into a control loop or reset loop, and you output a new airflow set point, okay, and then you compare that airflow set point to your min and your max. If it's below your min, you set it to the min. If it's above the max, you set it to the max. If it's anywhere in between, it's anywhere in between. And that airflow set point then goes into your outside air control loop, which could be as simple as modulating a damper or a more complex sequence that's required on some air handling units, okay? And you end up with this within the limits of the airflow measurement error, okay? So this is a significant improvement. And that just brings me to this addendum AB, which, like I said, it's just recently approved. Probably most of you don't even know it's been approved, okay? And a couple things that I want to state that what they're telling you to do now, which is an improvement, but there's some problems that I'm going to explain to you, particularly when we go into actual operating, meaning we're not at steady state, okay? But at any rate, they say DCV controls shall maintain the zone ventilation rate no less than the building component when zone CO2 concentration is at its ambient or low outdoor level, basically. Upon a rise in measured CO2 levels, ventilation shall be increased proportional. So it's a proportional reset. It's not the perfect way to do it, but it is a better way than that deadband control that I showed you previously, okay? And so it's a proportional reset, This statement here is not correct. Because CO2 and ventilation are codependent, this will rarely, if ever, happen. And I am concerned about the language on this. It says, when the zone CO2 concentration is equal to the maximum CO2 concentration, the minimum zone ventilation rate shall be equal to its design ventilation rate. That is not necessarily going to happen. And I'm going to show you that in a few examples. Okay, but anyhow, addendum AB is an improvement. Okay, it does, one of the problems that I've had getting people to do our method that we wanted to do is that you'll end up with a CO2 level in the space that varies. People weren't ready to do that. Well, now if you follow addendum B, that's exactly what will happen. CO2 level in the space will vary. There's a couple other things that I think are noteworthy here. And it kind of helps with this one problem I'm talking about. Zone and system ventilation rates are not required to be larger than the design ventilation rate required by section 6.2 at design occupancy, regardless of CO2 concentration. And that has a lot to do, I think the intent here was they knew there's going to be measurement error, but it's also because of this codependence problem, okay? So that, you have an airflow measurement device in either your outdoor air intake or at the ventilation zone on DOAS, and then, you basically can say, hey, the CO2 level is higher than my set point, but you know what? I can show that I'm at the design maximum. That's great. And I was glad to see this note because I think this was very important. The CO2 values in table 6.1, which I'm not showing you table 6.1. Unfortunately, they give you unfortunately, they give you CO2 default levels, which are rarely, if ever, going to be what the correct CO2 level needs to be on a lot of these spaces, okay? And unfortunately, not everybody's going to understand that. They're just going to look at these CO2 levels and set them, okay? The other problem is they allow CO2 to be used on low occupant density spaces, which I'm going to show you is a very, very, very bad idea, okay? But anyhow, the informative note that I think is good, it says the CO2 values in table 6.1 are only for the purposes of implementing CO2 DCV. They are not intended to be and should not be used as indicators of IAQ. That's very interesting, but very true. So then the next thing comes up, is there a better way to use CO2? Okay, and I think there really is. And this is really how I had wished that addendum AB would have been written in terms of how you do the control, because standard 62 rarely tells you how to do something. They don't tell you to measure outdoor airflow rates and control them, but for some reason they're telling you how to do the CO2 DCV, and they're not even telling you necessarily the correct way to do it. Okay. But when you take a look at the steady state equation, if you're going back and you're making the assumption of steady state, which is again what everybody's doing, which is wrong, okay, and you are measuring, if you were measuring the outdoor airflow rate either at the air handler or to the ventilation zone, okay, in DOAS, you actually have one more piece of this pie, and when you have that one more piece of this pie, you can estimate the population. And again, we've been saying this. I've been trying to tell people to do this for 15 years. I don't know why nobody listens, okay? But basically, if you have, if you know the CO2 level, you know the outdoor airflow rate going into the ventilation zone, you can estimate the population, and I just showed the logic here. You measure the CO2, you measure the outside air, you calculate the population. It's very easy to implement on single zone. That's what I'm showing you here, or on DOAS. You calculate the required outdoor air for that zone. Again, establish the limits. If it's less than min, set to min, greater than max, set to max, in between, it's in between. It goes into your outside air control loop. And that results in this, which for those of you that are working under standard 62 or the VRP, this is a really good way to do it, okay? All right, I'm going to step out for a second here. I'll be right back. I want to look at the steady state assumption errors. I got some examples, all right? So I'll be literally right back. Okay, I told you that would be fast. So now we're going to take a look at some examples. And the examples are going to be a little tricky to look at, okay? Basically, some of this is material I've just kind of put together recently based on some old material I had. And it's not best suited for a presentation of this type. If you want to take a look at the individual slides, I think from the file that we sent you, I think it'll be better, okay? But just follow along with me. The fact of the matter is we're not at steady state, and we have to take a look at what that really means in terms of the ventilation that we're providing. All right, so what I've got here is we're going to look at a couple examples. I have lots of examples. We're going to look at a classroom example and an office example. In the classroom example, we're going to look at two populations. We're going to look at the design population and a lower population. The office, we're going to look at design population. Okay, and when you take a look at these two charts, okay, all right, the top chart is basically showing you outdoor air CFM per person. That's either assumed, required, or provided. I don't have the required there. It is the green line because I just didn't want to get the arrows all too tight together. I mean, assumed and provided is what I want you to see. The bottom graph is the total outdoor air required and provided, okay? The other thing I want you to look at is that the red dashed line is the instantaneous amount of outdoor air that you are providing, and the red is the time average over 1 hour, which is what's required by standard 62, okay? And so those are all associated with the left vertical axes, okay? The horizontal axis is time. We're not going to have the students go in and out of the classroom. It does make a difference, but I don't think it's important for this part of the discussion. The right vertical axis on the top is how many people are in the space, and you see it's 30 on the top, if you can see that small print. And on the bottom, it's the actual CO2 level, okay? And so I just want to go through this with you, all right? So this model that I have has the ability to bias the CO2 measurement. It has the ability to bias the outdoor air CO2 level. It has the ability to bias the CO2 production rate. It has the ability to bias the actual min and max airflow rates or measurement accuracy that you're using, or the effect of using fixed dampers. But in what I'm going to talk about today, you don't have any errors. We're just looking at if everything was perfect, what's the lag effect, okay? And that's really one of the problems with all of this, is that there's so many variables to get this across and people understand it. It's not that straightforward. Bottom line here is we're trying to provide the proper ventilation for a given population. Are we or aren't we doing that, okay? All right, well, when we do this two-position deadband control that's very common, that folks have been using for years, we don't do it, okay? Clearly don't do it. There's a lag problem of about 1 hour. If you're looking at that bottom graph, the provided outdoor air is significantly less than the required outdoor air for the first hour of occupancy, okay? And that's the average. I'm looking at the average outdoor air provided, okay? It's low. All right. The other thing that's important for you to understand, and one of the problems that I have with everything here, is just because you're bringing in the design outdoor air rate for standard 62 doesn't mean you're going to hit your CO2 set point, because they're codependent. In this case here, the set point's 1,000 parts per million. But if you look at that right, you look at the blue on the bottom graph, and goes with the right vertical axis, we're over 1,100 parts per million. I mean, that's allowable by the standard, but it's going to confuse people, because you're not going to be able to get to 1,000 parts per million at the design occupancy, at the design outdoor air in this particular example. Okay, so that's the bottom graph. On the top graph, there's a couple problems here. I show the outdoor air, basically the top graph is outdoor CFM per person. What you provided is clearly low, but there are people out there that believe that you can tell how much outdoor air CFM per person there is coming into a space simply by measuring the CO2 level. That is true at steady state. It's not true when you're not at steady state, okay? And so when you take a look at this, your calculated outdoor CFM per person is really high because your CO2 levels were really low. And you're like, oh, this is great, I have lots of outdoor air. No, you don't. You significantly underventilated the space for the first hour of occupancy. That is not a good situation. Now, when we go to the next example is using the proportional reset that this addendum AB has recommended. Okay, well, the proportional reset, okay, is still going to underventilate for the first hour. There's no way around this. Everything's based on steady state, okay? The values are a little bit different in the beginning. This is a slightly better method, okay? But it's still going to underventilate for the first hour. And then we look at the third one, which is our estimate using, estimating the population. It also underventilates for the first hour, okay? So none of these really meet the requirements of Standard 62, even though Standard 62 has said, this is what you have to do. This is one of the problems when a standard starts telling you how to do something, okay? It's simply, there's no way to provide the required outdoor air, okay, using CO2 because of lead, all right? So this is at the design population. Now, the real problem we've had is when we're off design, okay? So here's the same classroom. Some people would say to me, well, it's a public school, it never gets off design. Well, there are spaces in the school that do go off design, and people are doing this in university spaces and college spaces, which are often off design, okay? So now take a look at this, all right? Now, instead of having 30 people in this classroom, I have 10. Okay, and so I've reduced populations, and this is one reason why I should never do this during COVID. Okay, if you have reduced populations, because you're really going to underventilate. So if we look at the bottom graph, okay, the required outdoor air is the green, okay, and the provided outdoor air is the red, and you never reached the required outdoor air. You never provided the required outdoor air using this two-position deadband control that we've been using. And in fact, you significantly underventilated for the first almost 2 hours, okay? Your CO2 levels look good, but you weren't providing the proper ventilation rate. When we go to the Standard 62 Addendum AB proportional reset, and I can explain this to you if you want to know outside of this conversation, because the proportional reset actually has a tendency to provide more outdoor air between the min and the max. What you see here doesn't really look too bad at the low population density, meaning we actually are providing the required outdoor air, and in fact, most of the time we're providing more than we needed. When we look at our population estimation method that we prefer, it actually does underventilate a bit. Now, I do have some methods that we can improve this with, but today I'm just trying to show you the problems that you have, okay? So that's on the classroom. So now, offices, that's something that really bothers me, because in the Addendum AB put in a 1,000 part per million set point for an office space. You have a low population density, okay? It takes a long time to get to steady state. Okay, so in this case here, we basically when we're trying to do, this is at the population, the design population was 5 people per 1,000 square feet, and we were at 5 people per 1,000 square feet. So this is like the best case, okay? And we're using this to control ventilation in office space. We underventilated for 3.5 hours, and we significantly underventilated. Okay, if you look at the provided versus the required on the lower graph, we significantly underventilated. Okay, and again, that's a problem. Now, this is with the deadband control. Okay, but it's not really any better with the Addendum AB recommendation of just a proportional reset, and it's not really any better with the with the version that we like, which is estimating the population. The reason for this is we're not really at steady state. It takes a long time to get it to steady state when you have a few people in the space. I don't understand why folks don't seem to understand that. Okay? And yet again, if you were using, go to the top there, and you didn't understand this relationship, and you just simply went by the CO2 levels, you'd say, "Ooh, look at all this outside air I'm bringing in per person." It's not real. That's not what you're really bringing in, okay? So these are serious problems. It always brings me to this. It's like, there's gotta be some agenda here, okay? Because the standard clearly says, provide the breathing zone outdoor air for the population. But yet there's no research, no significant support for counting the occupants. Why? If you counted the occupants and you measured and controlled the outdoor airflow, whether it be on a recirculating system or a DOAS system, you'd be done, okay? Why is there no support for this, okay? I mean, you say, "Oh, you can't measure it." Of course you can. I mean, there's plenty of counting systems today. COVID actually improved that. There's a lot of good counting systems. We even make a counting system, okay? There's ticket counting systems, arenas, convention centers. They know how many people are in these spaces. I used to say casinos were the only ones who could use video imaging counting systems because they were expensive, but they've actually come down in price. Point of sale, why a movie theater? Like, why is a movie theater controlling the CO2 when they have a point of sale system that tells you how many people are in each space? It's the ideal way to do it. You know when a movie starts, you know when a movie ends. It could be any kind of theater, but you know when it starts, you know when it ends. It even works out well for multi-zone. Why are we not, multi-zone recirculating, why are we not supporting this? There's gotta be a reason, okay? And so I always tell people, think outside the box, okay? And when you do population-based DCV, it's really simple, right? You count the people, standard 62 is based on people, do the calculations, set the limits, control it, okay? You end up with this. I have 3-person uncertainty on that class, 1,000 square foot classroom, 30 students in it. I go up to 35 here. I show 3-person uncertainty. That looks pretty good, and there's no lag error. I just don't understand it. I mean, I understand it, but I don't understand it. Yeah, a couple good things though. Also, an addendum maybe. I did want to point this out at least. Maybe we can get people to do things better. I skipped this when I showed this slide previously. Other DCV control logic shall be permitted to be used where it can be demonstrated to comply with section 62611 under all expected operating conditions. Yeah, that's provide the breathing zone outdoor air for the population. So yeah, you can do this and meet the requirements of the standard. That's a good thing. Okay, when we come back, we are going to talk about monitoring system operation. All right, I'll be right back. All right, I just did your favorite presentation.
Which one was that?
Oh, you know which one it is. What do you think it was?
DCV,
TCV.
because that's your best stuff.
Yeah,
That
right.
was.
Oh, yeah, well, we'll leave that alone, but yes. Okay. Well, I think we've done this a few times.
We have.
You know, actually, it's not really a long day for me. It's a long day for you. I mean, you know, I'm not even letting you change the TV.
No, it's a pretty quiet.
I mean, it's like,
But
it's been snowing on the TV for a long time.
yeah, I've been knocking out some Christmas shopping though online,
Oh,
so that's good.
well, that's,
It's
I
a
guess.
it's a quiet activity.
Yeah, quiet activity. Yeah, I hope you're not using up my bandwidth. Yeah, that's all
I
right.
don't think so. Like,
Yeah.
I haven't been that crazy.
Well, you know, this happened. So we're so, this is rural South Carolina, okay? And it's so rural that
my internet here is DSL. It's basically phone. I mean, it's not dial-up, but
Not the best.
no, and it's actually we're lucky. We're the first house from the main box, so it actually is faster the closer you are to it. People down the back here, maybe they're not even using it. I don't know, but there's not a whole lot of options when you get into rural South Carolina. I mean, the closest, like Walmarts and
It's a half hour, Camden.
Camden, I guess, is the closest. It's 35 minutes to Walmart. It's like 45 minutes to Columbia.
Which is nice until you forget something, and then
It's nice until
it's
you
not
forget
so nice,
something. It's an
but-
hour. Yeah, it's an hour to Charlotte. So last weekend we had to go to the Charlotte for the ACC championship game, and we were running kind of a little bit late. We had some customers up there, and we're driving down the road, and my phone gets a text that says
you're not gonna
I am
tell.
going to
Oh
tell
my
them
gosh,
that
that's
my
so
that the
embarrassing. It's terrible.
that the refrigerator is over 50.
Well, at first it was 45.
Yeah, well, yeah. So anyhow, what that means is Jessica's notorious for not closing the refrigerator door. It's one of those double door refrigerators that you have to kind of push. So here we are, we're going up there. It's, an hour 10, getting ready to go meet people, and the refrigerator's clearly open. So I called my neighbor. The other thing about rural South Carolina is you don't have a lot of neighbors. Or if you do, you might not want them in your house. And so you don't call anyone. So I called my neighbor that I really trust, and he wasn't around. So anyhow, Jessica ended up dropping me off in Charlotte.
Driving all the way back to the
I
lake,
had to come all the way back here.
closing the
Close
refrigerator.
the refrigerator door, and then go
Drive all the way back.
So she basically had 3 hours and 45 minutes of travel time on Saturday.
But I made good timing. Like I dropped you off at about 10 till 3, I think, and I was back in Charlotte at 5:05. So it wasn't like considering.
Well, you were speeding. I mean,
Well, just a little
yeah,
bit, but
there's just no way. But anyhow, we're down to the 2-minute warning again. And I should be able to get another break in. It'll be tight, but I should be able to get it in. So we got 1 minute left. If you look at that Morgan clock, you'll realize Morgan was pretty old. He's going to be 18. So
yeah.
he was up there. It's really not good how it happened either. I was going to get my thyroid removed, and he had to go to grandma's, and something seems to always happen when he goes to grandma's. I mean, he's come back with broken legs. He's come back with.
It really is funny. Like, it's not funny, but it's funny now. It wasn't funny at the time, but there were a lot of times, anytime we were gone for like a week or two, it was always an issue. Like something crazy happened, and Morgan had an injury.
Yeah, well, this time he had like more than an injury. So
Yeah.
this is, I don't know. But anyhow, all right, time's up. Let me go back and finish things up, okay? And then we'll see where we're at. Let's see if we can squeeze another break in.
Sounds like a plan. I'll keep my shopping.
Sounds like a plan. Mm-hmm. I feel like I might take this.
Okay.
I don't
deal. I've been finding some pretty good deals.
Good. Okay, we're going to finish up the why measure airflow rate portion of this by just really another brief conversation here about monitoring system operation. Let's take a look at it. All right. Basically, I've been thinking for a long time that we have monitoring for control, which is one thing, and monitoring to see how the building's working, which is another thing. And I look at those very differently. Okay. When I'm monitoring for control, I want a very accurate measurement at the point that I'm controlling. And when I'm monitoring for, just overall, how is the building operating, I want a lot of points. And yeah, I'd love them to be the most accurate points I can be, but I want them to be my eyes. If I'm a facility person, I'm understaffed, I want to see how my building's working. So I want to have these points all over the place. So, you're going to find that over the next year or so, I'm going to be talking a lot more about monitoring and some things that we're doing, both at EBTRON and our sister company, Greentrol. But today, this is an EBTRON conversation, so I'm going to keep it to EBTRON. But the facility managers need help, okay? And like I said, this is just a couple slides. This is just real quick. But you want to monitor key parameters in the building. You want to detect system faults so you can be proactive on these repairs and maintenance. That's where my head's at. I mean, obviously, you can also use these monitoring points to tweak your controls, okay? But I like the idea of, I want to control with very accurate measurement. I want to keep my controls somewhat simple, but then I want to monitor a lot more to see if my control is actually working. But not just is my control working, are my systems working? We have too many systems out there that just the facility people are overloaded and they just don't know if they're working, their systems are working or not, okay? And so from the EBTRON perspective, our monitoring capabilities are on airflow, total airflow rate. There's a lot of total airflow rate places that I'd like to know where the flow is. There's cases where I want to look at the individual sensor node airflow rates to see if there's something wrong, if I can detect some problem there. Temperature, we have velocity weighted temperature, so that's the best temperature we're going to be able to get. We also can look at individual temperatures, sensor node temperatures, so there could be value there. We have humidity as an option, right? So we have velocity weighted humidity, we have dew point, we have velocity weighted enthalpy. These are things that I might be interested in. Bleed airflow. We don't talk much about bleed airflow. It's I'll mention it in the next segment here a little bit, but we're measuring airflow bled from one zone to another zone, and it's a way to look at really pressure differentials, but very low pressure differentials. We also pick up temperature with that, and then we also have occupancy. So we have a sensor for measuring, number of people that go through a door. So that's our monitoring capabilities. The benefits of this monitoring, there's a lot of them, but I'm going to just kind of summarize them here. Outdoor air intakes, just simply verify that dampers are working. Verify that the minimum ventilation rates are being maintained. Verify your economizer is operating. On the fan, make sure your fans are operating properly, and particularly fan arrays. You want to verify room air changes. You might want to monitor coil performance. You might want to detect filter loading or failure there. Pressure, whether we're measuring pressure by looking at airflow rates or bleed airflow, which I have kind of the next half of the slide, we need to know, are the ins more than the outs, if that's what our goal was. Are we measuring these things? Are we getting feedback on it? Energy heat recovery ventilators, you can monitor performance. You can detect desiccant wheel frosting in cold climates. You can make sure that your devices, your ERVs and HRVs are staying in proper airflow balance. You can pick up filter loading or failure. Data centers. I don't talk much about data centers, but I've done a lot of work, as our company has, on data centers. And there's some really interesting things you can do there besides just, using airflow to control pressure in data centers, the fact that we have the individual airflow and temperature points gives you some real advantages in looking at what's happening to some of these server racks, or their hot spots or their low flow problem spots. Bleed airflow. I don't like to control to bleed airflow, but I definitely like to monitor, look at my envelope leakage, and see what's going on there. Verify pressure compartmentalization between critical containment zones. I like that, okay? We don't really talk enough about it. All right, we're going to go into why choose EBTRON next, and that's going to be where we kind of finish this thing up, okay? So, again, I'm going to stop for a minute, maybe more than a minute, and then we're going to come back and talk about why you should choose EBTRON, okay? All right. Okay, we're finally to the end of this. We're going to talk about the why choose EBTRON. So that's my little kind of sales pitch here, I suppose. Basically, there's 3 reasons why I think you should. Performance is a very important one, quality and value. Okay, so let's go and take a look at this and go into a little more detail, all right? First of all, how does it work? How does an EBTRON thermal airflow meter work? And, I'm not trying to tell you how to make it here, but I'm trying to tell you enough to understand how it works, because I think it's important if you specify or use something to have an idea how it works. So basically, if you take a look at this, we have that on the right side, the diagram on the right there is like a cross section of one of our probes. Even though we're showing a probe, all of our airflow meters work pretty much the same way. And so at each sensing point or sensing node, whatever you want to call it, there's 2 thermistors. And one thermistor, we put a little bit of current through, and it self-heats the part, and so that there's power dissipated in the airstream. And the other thermistor, we pass virtually no current through, so it's pretty much a zero power device, and we use that to measure the temperature. And so that when you look at how a thermal flow meter works, if you know on the heated sensor, for instance, if you know the power, which simply voltage times current in a DC circuit, you know the power. And because they're thermistors, we know for the electrical resistance what the body temperature is. So, basically we know the heated temperature sensor, the heated sensor temperature and the ambient sensor temperature. So we have this really simple relationship that relates power in delta T to velocity or mass velocity. And yeah, it's a little more complex than that, but honestly, that's what you need to know. And then from the the thermistor perspective, that's really the big deal with the EBTRON. We use a bead and glass thermistor. It's a handmade part. We're the only ones that actually use it. Okay, and it's because it's somewhat complicated to use. It's not like one of these chip thermistors that you're using in wall stats. The only thing similar here is the word thermistor. Okay, so we call them bead and glass thermistors. Big is a way for you to remember it if you want to. They're designed to handle extreme temperature changes rapidly, more than we would ever see in HVAC. They're hermetically sealed for long life. I mean, basically what you have is the thermistor substrate, glass, some leads. They're all matched so that they expand and contract the same. The glass is melted over the thermistor. It becomes hermetically sealed. One of the things that really differentiates the type of thermistor we use over anybody else's, or what you're used to using in wall stats and things like that, is these go through a significant oven aging period to stabilize them. Okay, so that's really one of the key parts of using this type of thermistor. They're very, very stable, but they're also very, very variable, and that's why most folks don't want to touch them. Okay, you have to individually calibrate each one for resistance temperature characteristics. You have to put them in multiple controlled temperature circulating baths. It's not an easy process. It took years and years for us to figure out how to do it. But that is what we do to every single part. And then once we have that, we pot them with a basically an epoxy. It's a marine epoxy, so it's a waterproof epoxy to protect the sensor leads and the sensor itself from water, salt, atmospheric acids. Okay, so it's a big deal. Bead glass thermistors is something you want to pay attention to with EBTRON, because when you look at the competitors that are out there that are using thermistors, none of them are using bead glass thermistors. They're all using chip thermistors. Chip thermistors are a relatively inexpensive part. They don't necessarily have the stability of the bead glass part, particularly when you heat them. Okay, and so basically what we have going on there is that we have these, our competitors using a chip thermistor, which is a lot less costly than actually what we're doing. But you want to keep that in mind. And if you understand the value of the bead glass thermistor and you're an engineer writing a spec, or even if you're not an engineer but somebody that's selecting the product, I mean, basically here's the major requirement. Each sensor node shall consist of 2 hermetically sealed bead glass thermistors. Devices using chip thermistors of any type of packaging are not acceptable. And quite honestly, you hold that part of the spec, you're done. And then just for to keep out the platinum RTD type devices, we also add devices using platinum wire RTDs or similar hot wire devices are not acceptable. We don't really see a lot of hot wire devices, arrays in HVAC, but they do show up from time to time. Okay, so very important. The other thing is all these thermal flow meters, doesn't matter what they are, who makes them, they really need to be calibrated, because there's variability between them, between each one. Okay, and so what are you calibrating it to? And what we do is we calibrate everything airflow wise and temperature wise that we do to NIST traceable calibration standards. And we don't go to a third party NIST traceable lab. We actually go directly to NIST in Gaithersburg, Maryland. We actually accompany our flow standard. They give us a report on calibration, and that's what you're seeing here. It's another one of these slides of mine that are difficult to see when you're doing a webinar. But if you take a look at it, you'll find out that what they give you is the NIST airspeed. And the NIST airspeed in this case is to a laser Doppler anemometer that they have. And then you have, that's the most left column there. And then the next column over is our unit, okay, the unit under test. And they give you those 2 readings, which is the average of so many data points, and then they give you the ratio of the 2, which is essentially the error. Okay, so that when you look at let's just take the first couple points there. 0.995 means it's a 0.5% different. 0.001 means it's 0.1% different. Okay, and then the column all the way to the right, expanded uncertainty, has to do with the standard deviation of the data sets. Okay, and that's how you start this traceability. Okay, so that's what we do. All right. And so, and again, to my knowledge, we're the only ones that do this, and we're doing this on a sensor basis. So we say provide a copy is another good spec item for you. Provide a copy of the NIST calibration report for the reference standard used to calibrate production tunnels, used to calibrate individual sensor nodes. Reference standards calibrated to third-party NIST traceable labs are not acceptable. That's only because there's another layer of error there. And devices claiming AMCA certification are not acceptable. The whole AMCA certification thing is totally different. I mean, you really only have to certify one unit. It's I'm not even going to go there today. Okay, honestly, this is what we like to do. The NIST is really the highest level there is in the world, honestly. So we have documented accuracy. What we do is we transfer the calibration to our tunnels. That's somewhat of a trade secret how we do that, what we're doing. But we have these production tunnels where each sensor node is individually calibrated, okay? And we calibrate them. What we call a calibration probably really isn't what most people think of calibration. We collect data on them, and we collect data on them at 16 points. 15 airflows plus 0 on a standard ducted probe like Gold Series or Hybrid Series probe. They go to 5,000 feet per minute. Fan inlets we calibrate to 10,000 feet per minute. We have some smaller units that we do a few less calibration points. They go to 3,000 feet per minute, but basically it's a multi-point calibration, and the result of that multi-point calibration is percent of reading accuracy. Every one of these sensors is barcoded and serialized because everyone's a little different, okay? All right, and then if we take any individual sensor node and put it back and do a report on calibration, this would be a typical report on calibration. All of the uncertainties are less than 1%, typically less than 0.5% of reading. And that's how we make our statement of the flow meter's sensor accuracy is better than 2% of reading. All right, so that's where that comes from. All right, so another thing you could say is each sensor node shall be individually wind tunnel calibrated. Don't let somebody mislead you and say they tested a unit at 20 points or 25 points. They may have only tested one unit to become, for instance, AMPA certified. We do this to each sensing node. You have 16 sensing nodes in the unit. We have 16 different calibrations, okay? So 16 points in this traceable airflow standards and have an accuracy of plus or minus 2% of reading over the entire operating range. So it's percent of reading measurement. To compare, I want to do this comparison. I've kind of added a few slides to this to kind of help people understand the differences in technology. So the raw signal, this isn't the output signal from your transmitter. This is the raw signal that we're looking at. For an EBTRON thermal sensor, is this pretty much, it's a square relationship, okay? And if you look at this, as the airflow decreases, the sensitivity increases, which is great for HVAC and great for outdoor air intakes. If you compare it to pitot arrays or air wings or piezo rings or any other differential pressure device, which has a totally opposite relationship where the sensitivity decreases as the flow goes down, meaning you don't really want to use differential pressure on low flow HVAC applications. You do want to put them on airplanes, okay? That's a good application for like a pitot tube, okay? But there's a big difference there as the sensitivity turns down. And actually, if you look at today's transducers that are used, pressure transducers that are used on all of these DP devices, okay, they're all percent of full scale devices. Accuracy in terms of, percent of full scale accuracy. And what that means, we have the sensitivity that's decreasing, but now we have an additional problem, which is, and I'm picking a 0 1/4 inch transducer here, but it's any of them. It could be 0 to 25 inches. So you have, a certain pressure gives you a certain flow or max full scale velocity. And there's an error associated with the pressure transducer that's not a flow error, it's a pressure measurement error. And so it's a percent of full scale number. And that imparts some uncertainty on flow. And then typically you're not running at the full scale of the application, or the full scale of the application is not the full scale of the pressure sensor, so you're a little bit lower, and you may have some turn down. In this case, I'm showing 3 to 1 turn down, which I don't think is a lot of turn down in HVAC for anything, supply, return, outdoor air. I don't think it's a lot of turn down. So this here I have 3 to 1 turn down. Well, what you need to understand is percent of full scale uncertainty means that the error is the same, or potentially the same, at turn down. And now when you take a look at that uncertainty imparts a much larger error. In fact, when you look at differential pressure, and it doesn't matter whose it is, if it's pitot tubes, air wings, if it's piezo rings, if you're doing pressure drop across a louver, whatever you're doing, when you take a look at this, because it's percent of full scale and it's also a square root relationship, you'll find that the error varies with the square of the turn down. That's a big deal. So 4 to 1 turn down is 16 times less accurate. In fact, what I've done here is I just show different percentage of full scale uncertainties and with turn down. And the little dash line there is plus or minus 3%, which is what you would get out of an EBTRON that's properly installed, right? And you can see you're nowhere near that. All right, and you might say, well, no, my pressure transducer is 1% or 0.5%. Yeah, but you also have to look at the temperature coefficient of that pressure transducer, and you also have to look at annual drift, okay? So the errors can be larger than, what you think, but the bottom line here, you have to understand, 1% or 2% pressure transducer is not a 2% flow error, okay? So take a good look at that chart. It's not hard to do these calculations either. So if you need me to help you figure out what it is, I'll tell you how we did it. Vortex shedding, I don't run into a lot of vortex shedding, but we do run into it in some areas. So it's like the deal with vortex shedding is that the actual raw signal is linear to velocity. Now, not to mass flow, to velocity. And that kind of sounds good to people, but it has one problem, and that's at the low, it has more than one problem. At the lower flows, it really becomes unreliable under 400 feet per minute. Okay, and so you really can't measure there, so you shouldn't apply it there. The other thing is the vortices that are shed are low audible. So you can get some problems with vortex shedding with background noise, all right? So that when you look at everything here in terms of what's going on, the EBTRON is the most sensitive device, and therefore the EBTRON is the best accuracy with turndown, okay? All right, the other thing that we want to do is just talk about sensor node ruggedness. So we talked about the marine epoxy that we use. Our sensors are sent out to independent lab to make sure that they can withstand saltwater exposure and they can withstand, acid exposure. And the reason for that is we get into a lot of environments, particularly outdoor air intakes, where we have a salt environment, where we have, sulfur dioxide and things like that in the atmosphere. And you need to make sure that these flow meters don't fall apart, okay? So we've designed them so they can handle that. That doesn't mean that in some areas you're not going to get salt buildup. There's some issues in super salty environments that you got to watch, but we want to make sure that nothing gets damaged beyond repair, okay? So that's something that we do that I don't believe our competitors would actually survive this test. So you can also add to your spec, thermistors shall be potted in an engineering thermoplastic assembly using waterproof marine epoxy. Doesn't have to be that, it could be anything they want actually if it works, and shall not be damaged by moisture, direct contact with water, or exposure to atmospheric gases. Provide a copy of an independent laboratory report to verify compliance with this requirement. I think that's fair. Okay, so saltwater and chemical resistant. Construction excellence. We made a decision a long time ago that we're just going to build the best thing that we can. I had people tell me back in the early 90s, mid 90s when we were doing this that we were nuts. That why are you gonna do this? It's overkill. Well, here we are, 2020, going into 2024, and we're still here. So that's a good thing, right? And so if you want to quickly go through, we talked about the sensor node with the beam glass thermistors and how they're potted. But inside these tubes, we use Kynar coated wire. It's very abrasion resistant wire, so it doesn't short out over time. We use a very strong aluminum alloy. It's lightweight, it's anodized, it's easy to handle. The mounting brackets, we use 304 stainless steel mounting brackets because we're going on a galvanized duct in a lot of cases. We don't want an aluminum bracket there, so that's a good move. The cables are FEP plenum rated, okay? Plenum rated, it's the highest level plenum rated cable. FEP is basically generic Teflon, it can handle much wider temperature ranges than you're ever going to expose it to, as well as ultraviolet light, okay? And then we have positive locking connectors, and on the Gold Series, it's all gold plated, right? It's just a no compromise construction approach. In terms of sensor node averaging, every sensor is individual. So the calibration data is stored in a one-wire serial memory chip at the end of the cable, so that even though they're different, you don't have to match anything up. Everything is plug and play. So you plug it in the transmitter, it's all converted over. What we're doing then for each sensor node is converting those two thermistors over to voltages over to binary. We'll push and shove in numbers. We calculate airflow for each point. We calculate the temperature for each point. We average it. We output it. I want you to think about it this way when you're buying an EBTRON. If you have an EBTRON with 4 probes, 4 sensors per probe, that's 16 sensor nodes. You've essentially 16 airflow meters and 16 temperature meters. because they're all independently calibrated and they're all independently processed, okay? So it's true sensor averaging. Again, you're going to compare that to some other technologies. I'm going to put pitot arrays in here. You know, pitot arrays are not averaging flow meters. They're averaging velocity pressure meters. Okay, pitot tubes, if you're an air balancer, you're doing a pitot traverse. For each point, you're taking the velocity pressure and then the square root of that velocity pressure. But an averaging array is not doing that. An averaging array, the best it's going to do is give you the average velocity pressure. And they're not mathematically equal. And just to make it easy, I'll stick some numbers in for you. So here would be something that we might see off of an elbow. So, you know, maybe the one point's at 2,200 feet per minute, and the next is at 18, and the next is at 5. You'll see velocity profiles like that. I'll see bigger velocity profiles than that on outdoor air intakes. I've seen 10-to-1 velocity profile on an outdoor air intake, okay? But in this case, so this is closer to 4-to-1, okay? So in this case, you take the velocity pressure at each one of those points, okay? Because that's what you're doing, and you would calculate that the average flow is 1,500 feet per minute. The best that an averaging array is going to do for you is give you the average of the pressures that it sees. So that average of those three pressures that you see there is 0.173, and if you calculate the flow based on 0.173, you get 1666. You're 11% off before you even use the pressure transducer, even though folks will tell you, they'll say, oh, it's a 2% flow meter. Well, it's really not necessarily a 2% flow meter. And if you come to EBTRON, we'll run this elbow test for you. This is just a summary of the elbow test. So we have a reference position. It's in a pretty good position. And then we go to position 1, which is 6 inches from a transition. It doesn't meet our guidelines. It doesn't meet anybody's guidelines. We have another position 6 inches before an unveined elbow. It doesn't meet ours. It doesn't meet anybody's. 6 inches downstream, 30 inches downstream. We'll do this with the EBTRON flow meter. We'll do this with pitot array. We'll do this with other thermals. But right now I'm just going to show you two things. Okay. The EBTRON at the reference position reads around 960 feet per minute. When you look at the other points and compare it to the reference, you're getting some pretty small errors. Remember, these things don't meet guidelines, okay? If I take the pitot array, do the same thing, look at those errors. They're huge. Well, the reason is averaging pitot arrays don't really average velocity. Now, if we get far enough downstream, we get to a good straight run, no problem. And we're doing this with a very high performance industrial pressure transducer, something that exceeds what you would use in HVAC. Okay, fan arrays, their averaging is a little bit different, but I can show a lot of different things with fan arrays. I can show that the way that the air enters the fan affects the way it measures, but in this case I'm saying what happens when you're basically putting all your fans in parallel or series, or however you want to look at it, when you're connecting them all together to one transducer, which is a bad idea, by the way. Because if you lose one fan, you have a huge averaging problem. Here it's the same kind of similar situation that we talked about before. Here we have fans that are operating and one of them is failed, okay? So, it's reading 0, okay? And if you take a look at this, you're going to look at, hey, the actual average flow, in this case it should be the total flow because I'm actually showing it in CFM, is 6,000 CFM, but if you use the average pressure from the fans, to a single transducer, you'd end up with 7,300, you'd calculate 7,348, you'd be 22% off. And that's just not a good thing, okay? So if you're gonna use fan arrays, I'm probably plugging somebody else right now, but if you're going to use fan arrays and differential pressure, which I don't think is a good, with piezo rings, I don't think it's a good idea anyhow. But if that's what you're going to do, if you still have these turn down problems, if that's what you're going to do, you better make sure that you have a pressure transducer on every single fan, okay? The other thing that kind of comes up, it's worth talking about right now, because we kind of get tired of hearing people talk about this. Our flow meters do not affect fan performance. This is a plenum fan. This is a Greenheck QXP 24 plenum fan, okay? And it's running without anything in the fan inlet, okay? And so that's top left. You go to top right, we're showing what fan speed we got it at and what the current draw of that fan is. The bottom left is an EBTRON located downstream in the duct system, okay? All right, and the lower right is the sound level. So we've got 10,250 CFM of air at 90 dBs, the way we did this test, all right? Nothing in the fan. Now, we put a pitot array in the fan. I totally agree. There's a problem. There's a lot of blockage there. It's in the small throat of the fan. You'll notice that the current draw went up, the flow went significantly down, and the sound level went significantly up. But when you do this with our EBTRON product that's made for the fan, for plenum fans, there's really no difference. So don't let anybody tell you you can't measure in fan inlets, right? It affects fan performance. Some products will affect fan performance. Our product will not affect fan performance, all right? When you get into our product and talk about connectivity, we've got it all covered. We've got isolated analog outputs. We've got RS-45. We've got Ethernet. Basically, they can be configured as BACnet or Modbus, and we have LAN. I will say the LAN we're not seeing much of. So if you've got a LAN job coming up, you probably should talk to us about it. Other things that we can provide, well, one thing we provide as a standard benefit is this velocity weighted temperature. Just the easiest way to look at it. I mean, it's a little more complex than this, but just look at this. Let's say we had we have an airstream, and the bottom half of it is 2,500 CFM at 70 degrees, and the top half of it is, 5,000 CFM at 80. If you go with the best averaging temperature meter you can get, you're going to get 75. But the reality is you have twice as much air moving at 80. So the real temperature is 76.7. So with an EBTRON, you get velocity weighted temperature. And that's really important if you're using this equipment. I try to promote measurement in air handler cabinets. You might want to be using this to also get discharge air temperature. You might be using this in outdoor air to make an economizer decision. It's a superior temperature measuring device, and it's provided with the equipment. If you want to add something, we actually have a humidity sensor that you can add. And with the humidity sensor, the device can be configured to either output velocity weighted humidity, which velocity weighting is very important for the same reason that velocity weighted temperature is. It can output dew point, and it can also output velocity weighted enthalpy, which is huge. It's a great thing to use if you're trying to do economizer switch over on enthalpy, because enthalpy sensors are really not all that good. And one of the reasons they're not that good is you're just measuring at one point. I mean, there's a drift concern on a lot of these sensors, but if you look at it in reality, you're not sampling enough of the air. Okay, so you're able to do that with our product. It's a small option add. Here's the same example that I used before. Now we're just going to be using it to look at RH and enthalpy. Let's just say that the enthalpy sensor was located in the bottom, where the bottom probe is. If you look at that, if for whatever reason you did want relative humidity, it's 57.7%. The enthalpy is 26.6 BTUs per pound. If you were to get the average enthalpy, okay, you'd be what I showed there on the left, which is you'd have, the RH would then change from 48.7 down to 48.7. The enthalpy is 27.9. But it ends up that the real humidity and enthalpy comes from doing velocity weighted temperature. So the real humidity of that airstream is 46.2%, and the real enthalpy is 28.3 BTUs per pound. I mean, that's the difference between economizing and not economizing. And I also tell people when they go out and pull one of these in, and then test and balance goes out and checks, and they're like, oh, yeah, your humidity sensor doesn't match ours. It's like, well, there's no way you're going to match it unless you look at the actual raw sensor, which is what we tell people to do, because they're not using velocity weighted temperature. Okay, so keep that in mind. Special tools, Eblink Reader. I think it's a great thing. It's only available on the Gold Series. It's a phone app. It'll either show you what what you basically can see on the display, which is what you see there on the left. If somebody went in and adjusted an EBTRON, test and balance went and set some factors, you can actually turn it off to see what it really reads from the factory. We have another screen that is a traverse data screen, which is actually made for balancers, so it's showing individual sensor node airflow rates and temperatures. And then we finally have another screen That is kind of our diagnostic screen. It shows you what all the parameters are set to, goes through all of the diagnostics, all trouble codes, trouble history, and it's got this send to EBTRON service. So if you have a problem, just go out, capture the data, send it to EBTRON. Service will take a look at it, save you a lot of time. We tell everybody when they order one of these things, give this product, give each location a name up to 16 characters, because that's what will show up on when you go in and look for these devices. Otherwise, it's just a serial number. The serial number is not as valuable. So give it a name when you order it. When we do fan arrays, we add an additional screen, which is individual fan airflow rates. Okay, warranty and service. 3-year warranty, pretty solid. Advanced replacement policy. We're so confident that we don't have many problems that if you call us, work through service, they're convinced that we sent you a defective product, we will basically build you a new one and send it to you. Okay, before you send the other one back. And of course, we will ask for the other one back. We'll make sure that it really was warranty, but that's great. And I think this is going to be bigger and bigger over time. You call us, you get somebody on the phone, and when you go to the service department, you actually have somebody who answers the phone. You're not waiting days or weeks to get a service person. You don't have a service ticket. We will solve your problems for the life of the product. A lot of times people will call us, talk about problems. It's not even our problem, but we'll help you work yourself through it. Okay, so we'll call it the peace of mind, all right? In terms of the products, our reps are very well versed with our products. In our larger ducts, we have our gold and hybrid units. The gold series has definitely more features than the hybrid, as well as more sensing point capability. The gold series can do up to 16 sensor nodes. The hybrid can only do up to 4. There's more connectivity options on the gold than there is in the hybrid, but the sensors themselves are the same. Okay, the sensors and the calibration are the same. Outdoor air intakes, I crack up every time somebody says, "Oh, EBTRON doesn't have a product for outdoor air." It's like, that's what we do, okay? But we can pack, it makes you feel better, we say it's for outdoor air intakes. But we can also package it with a Tamco damper for their Air IQ product, which I think is great. There's 2 versions. There's the Air IQ and the Air IQ 2. Air IQ 1, which is the one on the left, is really designed for like stub duct, return duct, relief fan applications. It's got a 3-inch flare on it. The Air IQ 2, 1-inch flare. Entry flare is for outside air intakes. It's also a narrower package, okay? We have a bunch of application-specific products, and that is, our EF series. And so we have these U probes and T probes, and the U probes are made for small rooftop units. The T probes are made for terminal box size ducts. It's DOAS is a good application there. See on the right where we have the energy recovery unit, you can actually take that EF2000 transmitter and split it so that instead of having airflow and temperature output, it has airflow 1 and airflow 2, so you can get airflow on both sides of like the wheel, okay? Fan arrays, we can go up to fans, measure up to 8 individual fans. It's a good product for measuring in fans. We make the Fan IQ, which is a Tamco backdraft damper, and our flow meter. We also do quite a few of your traditional single and dual inlet fans. We have a product for that. Bleed airflow, hard to get into. I can have a whole presentation on it. It's a 1/2-inch airflow meter, measures airflow direction. It's really good for measuring and looking at small pressure differentials between adjacent pressure zones. It's not a pressure meter, it's a flow meter, okay? But it's really good for detecting small pressure differentials. We also made it originally so that it could control relief air dampers, basically make an electronic barometric damper. Occupancy, we have an occupancy counting device. But, it'll measure people coming in and out of a door. It goes over the door or in the door jamb, right? So that's what we got for products. I think reality is, we've been doing this for 40 years. We know what we're doing. There's a reason we're still here. So that's where we're at, I think it's good to be done with this presentation. I hope that you all, I don't know how I can say enjoyed it, but I hope you got something out of it. And at this point, I'm going to get off of this. I'm going to sit down. We're going to talk about our next steps, which are the wine tasting. For those of you that are able to join us with Kevin Sass over at Halter Ranch, I think that even if we were not able to send you wine, I think you should consider listening to Kevin. I call him Professor Kevin. He's one of the smartest people I've ever met. He's good at answering questions. It'll last about 45 minutes to an hour, and it's just a rare opportunity, I think. So thanks again. I'll see you in a minute. Take care. All right. Looks like we lost Jessica. And there's not that many places to go. Anyhow, hey, so thanks in participating in this today. I hope that you were able to watch it. I hope you were able to get something out of it. I hope to see the majority of you afterwards here with Kevin at Halter Ranch. I think it'll be worthwhile for you. Don't forget to make sure that your video's off and your microphone's off in the beginning. But after Kevin's done, feel free, if you want to stick around, to unmute your audio and let your camera show you, and we'll just kind of hang out for a little bit. It's this is something we enjoy doing, and I think we'll probably continue to do this just about every holiday season. I think it makes sense. So see you in a few minutes, okay? Thanks.